Can you send me?
Welcome to the Machine Learning, AI and Health Collaboration Workshop. So I am Nilanjana, an assistant professor in Department of Statistics. And first I want to thank the other organizers, Paula, Tamids, especially Drew and Nick, for making this workshop possible. So while you are still settling in, I will quickly go through the results of the registration form survey. And after that, Nick is going to give us an interesting presentations on the models of industry collaboration and how we can adopt it to academia. So in the registration form, we asked you the question, how would increasing some resources will benefit your collaborative efforts? Then we gave you a list of like 10 or 11 areas, and you had to choose for each 3 answers between high benefit, medium benefit, and low benefit. And this was the answer. And you can see that among all the resources, most of the respondents felt that they will benefit the most if they knew more collaborators from different fields. And from your answers, it seemed that one of the reasons is interdisciplinary research. Now, there is a lot of funding in interdisciplinary research, and for that, you need to know collaborators from different disciplines. Also, it seems that AI researchers said they want to get connected to domain experts to explore the applications of their methodologies. And for this particular area, we saw that most people thought it is high benefit, but very few percentage of people thought it is low benefit, like that is the red mark. And we can see similar pattern for 4 other areas, that is internal grant for hiring postdocs, collaboration within your discipline. Many people felt that, especially those working in interdisciplinary research, finding people with the same interest, that is also difficult. Also, we have interest in community and stakeholder connection and proposal development support. So for all these 5 areas, we see that most people think that is high benefit and fewer people think that it is low benefit. So therefore, we mark these 5 areas as the high benefit area that come out from the registration survey. Also, we left a blank space, and there you could write about other resources that you think important for collaboration between AI and health. And 5 more areas came up important for that end. First was more interdisciplinary working groups, shared software development environments, platform for collaborative coding and data analysis. And also you thought that access to bioinformatics resources, say patient biobank data, that is important. And you also need statistical staff support for navigating those type of huge and messy data sets. And also it was pointed out that having training on large language models, big data manipulation techniques that are important to make this type of cross collaborations possible. And finally, we asked you, what are the preferred outcomes of this workshop? And it turns out that most people prefer learning about opportunities and trends in AI and health research. But networking with other researchers was the second most preferred outcome, and increasing resources and infrastructure supporting research was the third preferred outcome. So this is where I will now stop, and I will leave the stage to Nick. So Nicholas Duffield, the director of Tamids and professor in engineering, is going to talk about industrial collaboration models and how to adapt them to academia.
Hey, thanks, Nilanjana. I think Drew's going to change over the slides. So I just wanted to mention that Nilanjana is one of TAMIS has a career initiation fellow program. It's a competitive program, and junior pre-tenure faculty can apply to this and propose an engagement of TAMIDs in the broad community. So Nilanjana received an award under this program, and her proposed engagement was this workshop. So we're very, very pleased that she drove this forward, and thanks also to Paula for working with Nilanjana and Drew for making this all happen.
I can use this.
Okay. Okay, so this talk is about how to connect people, disciplines, foundations, and practice. And before I came to Texas A&M about 10 years ago, I spent most of my career at AT&T Labs research, and you know, coming here, coming back to the university environment, I've previously been a professor in Europe, and let me make observations about the differences between the way collaboration is done in industry and academia, and perhaps there are some ideas we can bring in from industry that would work here. So let's look at academic models for connecting disciplines. So our assumptions here are superb people working in different disciplines, but we know that academic structure incentivizes narrow specialization. So how can we enable people to work together? So one of the responses is to bring people together in multidisciplinary work to solve specific problems. Grant groups together, and we know NSF and other bodies have increasingly soliciting proposals for multidisciplinary work, and many universities have been cultivating responses to these to prepare interdisciplinary sea grant programs. We have this at Tang soon. But the problem is, how can we sustain this engagement between disciplines beyond just the funding period? I think my experience in industry, there's a different model for connecting disciplines. So we have the same assumptions. There are great people working in different disciplines, but career incentives favor collaboration, knowledge acquisition, what I call skill diffusion. You learn a bit about what other people are doing, and perhaps you become a bit less of a sort of strongly peaked in what you started doing. But there's also another dimension. There are also superb people working between foundations and practice, and the career incentives to invest time on engagement and those pay off an impact. I mean, when I was at AT&T, I got a bigger bonus for connecting with people in my work, and also connecting people even if I wasn't involved in that work myself. And there's a crucial role for what I call central people, who can build teams and connect others with diverse specialisms and have enough knowledge to bridge both vertically, between foundations and practice, and horizontally between disciplines. And this enables, doing this means that not everybody needs to be the same to talk to each other, but there's somebody in the middle who can connect the different people with diverse knowledge and approaches. And one reference for this is Carver Mead's model of what he called the tool-thin engineer. This was in the context of chip design, somebody who knows a bit about everything from algorithms to. So what are the benefits and challenges of integrating across disciplines and vertically between foundations and practice? So I think what increasingly happens at the moment is there are lots of benefits inbound to the center. You have a project, people bring the strengths to meet in the center, and you assemble these diverse parts to accomplish a specific goal. But we need more sort of outbound benefits to the center. We have new foundational work that's stimulated by the practical requirements, and also practice adjusts to make the best use of this foundational work. And the disciplines are refreshed by importing new ideas and methods from, So the hardest challenge really is joining everything in the center. There's less certainty than in single disciplinary work, less clear how diverse components fit together. It's harder to anticipate problems, and friction means exploratory work may take longer across disciplines. So we've got different languages, different levels of abstraction, even different notions of what constitutes research. And the challenges of working in the center are often underappreciated at the edge. Something might be seen as mere applications or mere theory, not central to somebody else's work, depending on the point of view. And the risks and potential rewards are inherently higher than for single disciplinary research. But I think refreshment of the disciplines is crucial to the idea of sustaining momentum beyond the original problem what got people together. We want long-lasting research ventures and not just one-off solutions. So here's some recommendations. Universities should hire more people in the center, from industries, agencies, national labs, and mixed roles are okay. Be research active people who focus on building teams, management, administration, and give them enough job security to enable them to take risks.
Yeah.
And incentivize and support these integrative activities. In talking to a couple of people, recently I've seen, a certain sort of parallel ideas here. I'm talking with Ronja Basex from the College of Engineering, and Jim Coulson as well, here in health. And one idea is, coming out of this is really creating focus thrusts to which central people can gather project teams. And I think the key here is it's sufficient to make projects interdisciplinary, not necessarily the people themselves. It somehow takes longer to change people than put a project together. And even if established faculty are not interdisciplinary, students can become so. So that's sort of the easier growth path. And in the end, those students are going to become, tomorrow's faculty. So, things are going to become easier as time progresses. And I think we need to develop capacity for rapid interdisciplinary and vertical integration. These faculty-to-faculty connections take a long time to develop. All that friction, all that, establishing a common problem, talking the same language, figuring out what the contribution can be. I think we need to, we should still seek to hire interdisciplinary faculty and incentivize departments to hire. So sometimes, if you have a situation where an interdisciplinary faculty hire is competing with any other faculty hire in that department, it may end up not being prioritized. So what can the university do?
Perhaps we need to think about guidelines.
As far as data science and AI goes, one way you can bootstrap while you're waiting for this
interdisciplinary development to take place is bring in people who can at least
drive the work, drive the execution of the work, even if not the formulation. Statistical consultants, system specialists, developers who can be attached to the project,
either employed directly or employed centrally to private school.
So that's the end of my talk. And hopefully we can work together to drive some leads and it's fun.
Thank you.
Thank you, Nick. Howdy. Good morning, everybody. Okay. So I'm very pleased to be here, and I want to thank Nilanjana and Paula for the invitation. Actually, the invitation was originally extended to my boss, Dr. Jack Baldoff, who is the Vice President for Research. And Jack is unfortunately unavailable today, and I'm the next best thing, to Jack. But actually, even if Jack was available, he would have asked me to at least help with, his keynote, because I'm fortunate in my role as Associate Vice President for Research and Strategic Initiatives. I'm fortunate to be working with a lot of faculty groups on campus to advance some research initiatives, including AI. As a matter of fact, we hosted a university-wide AI workshop just 2 days ago. And Nick was one of the leaders that served on the planning committee. And so this is very relevant. It's really remarkable that we're hosting 2 AI workshops in 1 week at Texas A&M University. What does that say? It tells us that how important we take AI as a university. So what I would like to start with, and that's what I did at the last AI workshop 2 days ago. I started with a couple of bold statements related to AI. And I'm going to do that again today. If you agree with those bold statements, say gigem or thumbs up, okay? Gigem or thumbs up, okay? So AI is a transformative discipline that has the potential to revolutionize all disciplines. If you agree, gigem, okay? Any institution that ignores AI does so at its own peril. Gigem. All right, so we are all in agreement here now, so I can continue. So with that said, what I want to do is I want to quickly go over a few topics. Obviously, the focus is on AI and health collaboration, but to give some context to how we got here as a university, I want to, take us through a few things, like talk about our strategic plan for research and how that relates to this topic. And then I also want to, do a quick summary of Texas A&M University AI landscape. Many of you may not be aware of some of the activities that are ongoing that align with today's workshop. So, and then finally, I'll spend the rest of my time talking about, AI and health collaborations. So, our strategic plan, many of you may not be aware, we have a new strategic plan. The reason why I say many may not be aware, this is a big university. It's always challenging for information to go across, and then we are all bombarded with information because it's a huge university. So many of us don't even know which information is very important. Some information, are just deleted. So in case you are not aware, we recently unveiled a new strategic plan for the university research enterprise for 2023 through 2030. And the process started 2 years ago. And, and finally we have a strategic plan is on our website. And in that strategic plan, we try to define a few things. First, what is the mission of Division of Research? Because this is a huge university with different, components to it. We may not even know that Division of Research plays a central role. So Division of Research, we are a support and service unit. We coordinate research across the Texas A&M enterprise on landscape. We work with colleges, agencies, and units to advance research. So we're a central unit. We coordinate research across the entire enterprise. And our mission is to capitalize on our research strengths, okay? We're a very huge university. Last year, our research expenditure was over $1.25 billion. That is huge for a land grant, a public university. And so it takes a lot of coordination, all right? It's a big, our office, the Division of Research, we have over 600 employees, just to let you know. That is more than a university, some universities, okay? So it's a huge enterprise. So we capitalize on our research strengths to deliver solutions to serve the public good. Our role is to work with all of you and the units to grow our research, to build capacity through collaborations, which is essentially what we're trying to do today. We're trying to facilitate collaboration across disciplines and increase communication and enhance visibility. Again, many of you may have heard the new president, President Welch, talk about research identity. Have you, if you listen to his State of the University address, you heard him emphasizing research identity. What is our identity as a university? That's part of what we are doing. We're trying to achieve with this strategic plan. Again, I'm not going to go over this, but there's a lot of effort that went into that strategic plan. We received feedback from across the university. Incidentally, or interestingly, this room was used for most of our town hall meetings. So you remember, okay? That's interestingly. And the critical components of this plan, obviously, we are Aggies. We start with Aggie core values. We know that the realist values. We're trying to emphasize culture change. Culture change in the sense that, okay, how do we reward excellence, okay? Because that's not unique to our university. Almost every university is struggling with that. One of the things that we introduced to our strategic plan that has not been done in recent history is we try to go to that question of research identity. That was even before the new president talked about it. we try to say, okay, what are those big topics, big umbrella topics that we can, rally around as a university that will provide opportunities for us to advance our research enterprise and also elevate our stature as a university. So we defined some of those themes. And obviously, you can't do research without excellent infrastructure. So we focused on that. And then impact assessment. So the key is, okay, how do we assess impact moving forward? And so I just wanted to tell you, so again, we define those strategic research themes. Those are cross-cutting themes. Those, we came up with six themes that are listed on the top box there. Again, there's a lot of grassroots feedback that went into this. I don't have time to talk about it. It wasn't that I sat in my office or none of us sat in our office today. We received input from across the university. And then under each of those things, we define subthemes for a total of 21 subthemes. But before I show you those, so this is what I did 2 days ago. I said, okay, I asked ChatGPT, I said, what are the research strengths of Texas A&M University? And this is what it gave me. It says, we are renowned. At least that's a good word. We are renowned for a diverse array of research strengths. And then listed some of these, engineering and technology. And this is good. But you might notice that this is along disciplinary boundaries. But research nowadays, when you go to those agencies, it's not really along disciplinary. They're talking about interdisciplinary and transdisciplinary. It's about issues, not about specific disciplines. And so that's what we are trying to get through our strategic plan. And hopefully in the next 2 years, ChatGPT is going to redefine some of this as we rebrand. But again, some of these items, so these are the 6 big themes. Sorry, this two, but I'm going to share some of these with you. 6 areas: community, culture, and economic resilience. These are issues. Emerging technologies and innovation, health, and quality of life. Again, health is not disciplines. Issue, big challenges, grand challenges. National security, space, and sustainability and environment. And I want to look at health because we're talking about health here. We identified 3 sub-themes: diagnostics, disease prevention, community health. You can think about AI right there in all of those 3. Okay? And then under emerging technology, the first sub-theme is what? Learning. So you can see how this workshop aligns perfectly with our strategic priorities, okay? And on this table, we try to, identify topics with national priorities because that's where the funding is going to come from. And you can see that a lot of agencies are funding AI. See them here? And then we also try to align them with a map, with our internal capacity. What units, what centers, what colleges can play a big role in some of those. You see, AI is actually almost every college. And then you look at the health and quality of life sub-themes, you see a lot of colleges and centers. Again, what is this? Interdisciplinary, working across the entire enterprise. That's what it takes, and that's what it would take for us to get to where we want to be as leaders. Okay. All right. So fast forward. After we've defined all of those 21 sub-themes, clearly we cannot advance all of the 21 at the same time as initiatives. And so we had a university-wide committee that worked with the leadership to identify a few ones that we can advance for the next 2 years. And these are the ones on the list again. AI is on that list. Health, disease prevention, and health promotion. And you can see other priorities on that list. So this is where we are. Next year, we're going to do the same process. We'll come up with maybe it's a subset to advance, It's not like we're leaving anything behind, but we can at the same time. So, and that's where we are. And we started organizing workshops to advance those topics as strategic initiatives, and then looking for opportunity to fund that or make investments around those initiatives, okay? Now, with that background, AI, we know AI is a hot topic and a buzzword nationally and globally. And it's not because it is new, but because of new capabilities, okay? That's why it's so, an ability to transform, virtually every aspect of our daily life. That's why AI, it's really a buzzword now. And when we talk about AI, AI is more than generative AI. Everybody talks about generative AI, but there's more than that. There's a lot of other things like artificial general intelligence, artificial narrow intelligence. And we as Texas A&M University actually have a lot of strengths in this area that many of you may not be aware of. I'm, in my role, and that's what I love most in my role, I have the opportunity to interact with faculty from the entire campus. I lead a lot of initiative, the space initiative, space exploration. I work with semiconductor initiative. So that allows me to understand our capacity and capabilities. And we do have a lot of strengths. And one of the other reasons why this is a national priority is you can see a lot of federal funding agencies actually have prioritized AI in their funding programs. Same thing with private sectors. There's a lot of private sectors out there that are interested in funding AI R&D. And more importantly, our peer and aspirant peer institutions are developing initiatives around AI. It's not like we want to follow them, but we are leaders. We also want to exert some leadership. The key thing is we need to define what are our strengths, what are our niche domains in AI. Because if our AI initiative is exactly like John Hopkins, chances are we're probably not going to be able to compete with them, okay? So in terms of AI and health, the most interesting one that I found is the University of Michigan eHealth and AI initiative. And I would encourage you to visit that. That's actually in alignment with all of the things that you, Paula and Nilanjana, that you really want to accomplish here. A lot of the things that you have identified in your survey is actually part of that initiative. So they're doing a lot of things. So I think we need to study that and see how we might be able to learn from them. This is how they brand themselves. They call it eHealth, eHealth and AI. That's what eHealth means. Making University of Michigan a premier hub for AI and health to improve health using technology. That's how they brand themselves. Almost exactly what we're trying to do here. Okay, that's great. And our good friends in Austin too, they have their own AI initiative. So, and by the way, we are still the leading research university in Texas, okay? In terms of our research expenditure. So, UT is great, but still not as great as us, okay? All right. So, why do we need an AI initiative at Texas A&M University? For all of the reasons that I've mentioned and more. AI has the potential to revolutionize and transform all our fields and even our university operations, not only in research, but all our operations. It can drive innovations and economic development in Texas. That's actually, if we're looking for funding from the state, that's what we need to really hone in on, because how is this going to help the state, in terms of economic development? Workforce development is really important. Texas A&M has leading strengths in foundations of AI, post design of AI hardware, and AI applications. So this is one of the reasons why we need to work together to create a strength in AI. And like I said, AI and machine learning has been identified as a strategic priority for Texas A&M. So some of the efforts that are already ongoing on our campus regarding AI, we have a lot of activities that are ongoing. The provost office, is leading a generative AI in teaching working group. I'm part of that, and that's looking at AI in teaching. I'm leading, and with my colleague Xinyu. Is Xinyu here? Okay. I'm leading the generative AI and research working group with Xinyu to look at how we can, incorporate AI into our research the right way. And we recently released, there's a website on that topic, and we recently released some best practices for generative AI and research. I encourage you to review it on our website. That just gives us some, guidance on how to use, generative AI in research. And then we are also talking with Microsoft right now on maybe the development of a custom AI platform for Texas A&M University. So there's a lot of activities going on around that. In addition to that, we have a lot of programs and institutes within Texas A&M University that are focusing on AI. Clearly, TEMIDS, Nick is a leader there. HPRC, the Semiconductor Institute. And then we also have a lot of federally funded centers at Texas A&M that are related to AI, including those that are listed here. So we're not new to this. All we're trying to do is to, position ourselves to be stronger in AI. And what I did with Xinyu, who works with me as a faculty fellow, we looked at our Maestro data, and we just used the keyword AI and machine learning and all of that. We found over 600 active awards, okay? Total funding of over 600 million, okay? That's like $1 million per award, roughly, okay? That's a lot of, so it tells you that more than half of our research enterprise is actually AI related, okay? And a lot of the award relate to core AI and machine learning, foundations, but a lot relates to application, of AI in agriculture, arts, education, technology, environment, and health. There's a lot of health-related projects that already incorporate AI, okay? And also, we have 2 proposals right now that we're working on, for submission to the NSF AI Institute solicitation. Those are big, proposals, all right? We were invited, our pre-proposals were, approved, and they invited us to submit. If we can get one of those funded, that's great for our university. Just quickly, again, still talking about Maestro data, our Maestro data that relates to AI. You can see the sponsor sources. Even USDA, many of you may not know, but USDA has a climate smart agriculture program that funds a lot of AI in agriculture work. That's a lot of money there. Obviously, AgriLife landed a couple of those big grants this past year, so that's why. But you can see in terms of health, NIH, National Institute of Allergy, you can see those, General Medicine, Institute of Diabetes, those are some of the programs that are already funding AI-related work at Texas A&M University. And our workshop 2 days ago, this was the purpose, to organize and advance our efforts. And our aspiration is to emerge as a leader in AI development and applications. And we're working on the outcome now. We're working on a report. Some members of our senior leadership team are actually interested in the report. to understand what will it take for Texas A&M University to advance our AI initiative. So now, this is the last part of my talk, focusing now, zeroing on AI and health collaboration. We all know that AI, before AI, health was great. I mean, there's a lot of advances, in health, but AI has the potential to completely revolutionize healthcare and health. And you can see some of the opportunities. It's limitless, actually, but these are the big ones. Improved diagnostics. You all know, I feel like I'm preaching to the choir here. Drug discovery and development, remote monitoring and telehealth. So all aspects of digital health can completely, change by AI. Precision medicine, public and community health, even in the use of AI for disaster response and recovery. I actually like the fact that there's a talk today on that topic. And more importantly, to improve efficiency and reduce waste and reduce cost. So these are several areas. So that means the opportunities abound. And what we need to do is, as a university, to say, okay, what are those ones that we really want to be known for, okay, that we want to lead? Doesn't mean that we can't do everything, but, what are our strengths in some of these areas, okay? But there are some challenges that we need to overcome as a community, not at the university level only, but generally, globally. We all know data privacy and security is a big concern when you use AI or any technology. Workforce disruption. Many people who are already in the healthcare industry may not have that training, may require additional training for that, but that's opportunity there too. Bias and inequality, and that's inequality, that's actually a big one. So when you look at, there's already a lot of bias in our system, or inequality in our system, not only unique to healthcare, but most sectors. Now, unfortunately, AI has the potential to exacerbate that. So we need to be mindful of that as we develop programs. And then how do we integrate AI with existing systems? In what I call the black box syndrome, and this is what I made up. It may not be the right term for it, but I just made it up. And I'm the speaker. It's my right to make up things. Well, I call it black box because many of the AI systems, you really don't know what is. It could be garbage in, garbage out. You really don't know what there's no transparency. And sometimes it's hard for people to trust data that comes out of that system. So we need to deal with that. Obviously, regulatory and ethical issues are very important, especially when it comes to healthcare. So the purpose of today's workshop, Nilanjana has already outlined that. But what I want to emphasize is based on the pre-workshop survey. I want to address, I have a couple of slides more. I want to use that to address some of the things that came up from your pre-workshop survey. Platforms for connecting with cross-domain researchers. I'm going to allow Nick to address that at some point. But I'm going to address seed funding for research. I know faculty love seed funding. I'm a faculty too, so we love that. I love that too. So I'll talk about that a little bit. Increasing industry connection. Nick already addressed that. So computing resources. That's one of the things that came out of the AI workshop that we held 2 days ago. And we are compiling a list of those resources that are needed. And my understanding is the chancellor is also probably interested in, because, so we're taking care of that. Well, we know, we have an idea of what resources are needed across our enterprise. So I want to focus on the resources and support. So the division of research that I represent, these are the kind of support and resources that are available for you, not only for AI, but for a lot of our strategic initiatives. We can help you with team meetings and workshops. If you're building teams around projects, we can, we have a proposal development team that can help you with your proposal, and even red teams. Obviously, SRS, is available to help you, and we can facilitate that. Research compliance support, if you need that. Engagement with funding agencies. That's one of the things that we are increasingly helping with. If you need help engaging a particular industry or funding agency, we can help you. Then there are two relevant offices for AI and health that I want to highlight today. In the Division of Research, we are in the process of recruiting a VPR for health. So that tells you how important health is. We're going to have an AVPR that's going to dedicate his or her time on health, okay? And that will work with us and the HSC together. And that position is going to be working with me also to advance some of these strategic initiatives. So this AI and health theme is going to be one of the, low-hanging fruits, so to speak, for that position in my mind, okay? And then we also have an AVP Digital Health, Jim Cason. How many of you know Jim Cason, okay? So there's a lot of opportunity for those offices to work together to help support AI and health. Of course, TEMIDS, and Nick, by the way, Nick is a great, thank you, Nick, for your leadership. I have worked with Nick extensively in the last almost 2 years when I started in my role. My boss assigned me to provide oversight for TAMIDS and a few other institutes. And I have enjoyed working with Nick's, to advance TAMIDS mission. So we've been talking about how can we even leverage funds across the university to support AI. And so Nick and his team are doing an excellent work around that. So you see some of the things they can, some of the resources that are available. I think this is my last slide, or maybe, So I want to outline, you talk about seed funding, I want to outline some seed funding opportunities from the Division of Research. All of this can fund AI and other things, okay? The Targeted Proposal Teams, TPT. Last year, we funded 9 awards for a total of $4 million. And this is for team building around target funding opportunities. For example, if you identify a major funding opportunity that requires team building, you can apply to that. And this year, we're actually that was one of the things I convinced my boss, I said, we're going to use a portion of it as planning grants for major target funding opportunities in strategic priority areas, including AI. So we're going to elevate that and say, okay, if you have projects that you want to do around AI and you are pursuing a specific target, you can request planning grant to support team building, okay? We have the Research Leadership Fellowships. Last year, 12 awards and total of $900K. This year, we're going to go through that again. RDF, how many of you are familiar with RDF? It helps with core facilities and equipment. Okay, last year, 2022, we awarded 4 projects for a total of 4.32. So it's helping to improve our research infrastructure. ADM, how many of you are familiar with Advancing Discovery to Market? So that's one of the programs that I manage. This is to help you move your discovery to innovation and then from there to commercialization. AI should be a big component of that. Last year, we awarded 22 projects, a total of $5 million. And we have pre-proposals for this year that are due March 28, okay? Price, this is a collaboration between Texas A&M and Prairie View A&M. Again, I'm managing that too. Last year, we funded 15 projects, total of 600K. Proposals for this year are due April 29. So these are all funding opportunities that you can, leverage for your work on AI and other disciplines. All right. So in closing, I really want to thank the organizers of this workshop, because it is very important that we as a university continue to work together and facilitate communication and collaboration. Again, the take-home message from my perspective is that as a university, we have to define what is our niche, what are our niche domains when it comes to AI and health. And what do we want to achieve with this AI and health initiative? And what does success look like 3 years from now, 5 years from now, 10 years from now? So again, what are our niche domains? What do we want to achieve? What does success look like? Thank you for listening, and I want to thank you again for participating in this workshop, and I wish you a very productive deliberation. Thank you very much.
Well, welcome back, everybody, and welcome to our panel discussion on what makes a cross-disciplinary project successful. And we're very pleased today to have our 5 panelists, Paula Sharman, Gang Han, Bani Malik, Haishun Kum, and Ricardo Gutierrez Suna. And I'm going to ask them to introduce themselves briefly in a little while. What we're going to do is, after that, and I'm going to ask them to give a brief description of their background and experience or plans in collaboration in AI and health. And then, based on the survey results, we've distilled some questions concerning challenges in AI and health collaborations. And I'm going to pose those to the... I think we're going to have the questions up in a minute. I'm going to pose those to our panelists and ask their insights and success stories and challenges, and very much encouraging discussion between the panelists. And then we're going to open it up to questions from the audience. And we're going to have, Delaney is going to have in the corner there, who's our newest hire at Tamits, is going to be, have a roving with a microphone so you can ask your questions. So we'll start from this end. And Paula, would you like to go?
Howdy. So I'm Paula Shireman. I'm in the School of Medicine. I am a clinician and a researcher. So I'm a vascular surgeon, general surgeon, and a care specialist. And I have a clinic at the Health Hub where I saw a patient this morning before running to this conference. I'm a recent Aggie. I came in April of 2022. Previously, I was at UT Health San Antonio as, a clinician. I was a PI, multi-PI of the Clinical Translational Science Award, the CTSA grant, which is to like about 60 universities have these really big grants. And the Biomedical Informatics Core reported to me evaluation and implementation. The Biostatistics Core reported to me in that function. I am passionate about how we can improve health. And I have a project with Tracy Hammond where we have people at the Park at Traditions wearing smartwatches to monitor activities of daily living. The gray tsunami, as they call it, is coming. Our population is aging, and how we manage that population with aging in place strategies is going to be critical. I have had grants where we've had natural language processing as a specific aim. I'm working with a team with a VA grant where we're looking at machine learning to try to find variables that the clinicians might overlook or not really link. I am, like I said, I am very excited about all forms of AI and also equally terrified of them as a clinician and as a patient, because I was at Methodist Hospital yesterday as a visiting professor, and Epic has digital twins within their health, within the medical record, but we have no idea how good they are. So, and the clinicians themselves are going, I don't know to trust them. I don't know how to use them. So there is great great potential and great peril in what we're doing, and I am very excited to be a part of it.
Fantastic. So, hello. Howdy. I'm Bonnie Malik from Statistics. Is it too loud? A lot of times I don't need a mic, like, people are, at least my students complain, take it out. Anyway, so I'm from Statistics and I'm also a Bayesian statistician, whatever it means. And I'm also the director of Center for Statistical Bioinformatics. Recently, we have a center, an NSF Institute of Data Science, we call Tripods, which will expire this September, which was on foundation of data science. Nick was also a co-PI in that institute. So we have several grants, NIH and NSF, working on machine learning and AI. We work two separate things. One is the foundational issues of AI. We heard of generative AI, right? So there are 4 models of generative AI. They are used by ChatGPT, Google, depending on what they are. These are all statistical model or physics-based statistical model. We are working on the 5th one. You'll hear something very big within a year or so. So that's the foundational part of the research. On the other hand, we do application. Bioinformatics is one of the application where we do a lot of single cell data, and single cell based on genomics, proteomics, transcriptomics, all these things. I have my collaborator Tapasree here. She'll talk some of these things here. Rob also worked with me, Rob Chapkin. I cannot see him. He told that he'll be here, but anyway. Also, we work and then we try to predict cluster genes. We try to predict this, how long this cancer patient is going to survive based on your genomical expression levels and stuff like that. These are all predictive models. And I was really happy for 10, 15 years, last 10, 15 years, I'm doing that nobody can beat my models. But now all these deep models came back and they're, I don't know, these are black boxes that are fascinating, believe me. So we are trying to get into there, working on it in our tripods group. Some of the mathematicians, actually top level mathematicians like Ron DeVore and stuff like that, they work on the theoretical properties. They showed that why they work. They're not black boxes kind of thing. We are trying to mimic them in a more interpretable framework. So we are trying to do AI on interpretable framework. Rather than bioinformatics, we work on big nutritional studies, precision nutrition, as well as big health data, like, with business school, like, how to make policies when you have insurance data. Why people are refusing these shots, like, why they don't want to take vaccine. Millions of databases this insurance company shared with us, and we are trying to find out the reason, digging this data and trying to make some models, but these are policy models, so that's very important. Statisticians stop on analysis, AI stop on analysis. At the end of the day, somebody has to make the decision, and we try to see how we can go to this stage using data. And I'll stop here. Once I start talking, I never stop, but this time I'm passing it to the next guy.
Hi, I'm Ricardo Gutierrez. I'm a professor of computer science. I've been here for 22 years. The research, the interface between machine learning and sensors, I've worked on for the past 20 years, mostly on wearable sensors. Before the Fitbits and all that, we were developing our own sensors and torturing subjects wearing this outside of the lab. And speech, I've worked on applications of speech for language learning, for apraxia, motor disorder for children. For the past 10 years with Jerry Cote's group, I've worked on diabetes research using continuous glucose monitors, physiological sensors. I want to emphasize that AI is statistics, and the statistics cannot happen without data. So I think any initiative that doesn't consider the need for data is going to be problematic. I think about 2 regimes. One is the big data regime, where you see things happening in large language models and speech and vision that have the advances have been possible because of massive amounts of data. And the small data regime, which is what most of us have been doing for our entire careers. What else? I'm at the kind of like an AI practitioner or a machine learning practitioner. I think it's important to also define what we mean by AI. I think you did a good job at emphasizing the three: the general AI, the narrow AI, and the generative AI. I think we're here mostly because of the latter, the impact that ChatGPT has had on the public perceptions. But there is all the others that we also need to consider. And I'll stop here. Thank you.
Howdy, my name is Gang Han. I'm in School of Public Health. Probably I don't need it. In biostatistics, I'm a biostatistician. I collaborate literally with pretty much everybody, which all the in the health extensive amount. Been here for 8 years and knowing more and more folks and collaborators is in statistical methods. I've been working on early days, the computer simulation codes and building statistical emulators for predicting the outcomes for those codes. Personalized, which has also AI components, especially the clinical trial and outcomes. I work on in computational algorithm for Bayesian statistics, which is an essential part for recursive learning in the. And these days, the AI booming. And 3 days ago, media announced B200. And who is Blackwell? He's a statistician in my major. I think all the statistics department know theorem and optimization procedure for computing. Basically, that's a part of my research. My point is, I think is the statistical method a key part in it, and I'm glad to be part of it.
Hello, I'm Hye-Jung Kim, and I'm also at the School of Public Health with him, but I'm in the Department of Health Policy and Management. My PhD is actually in computer science, similar with Ricardo, in data mining. I've been doing, I guess I have a PhD in computer science, but in the process, I also minored in social work, macro social work, so I studied policy and management. So it's been 25-ish years of me doing computer science plus policy and management in different realms of health and social services. So most of my career has been in team science and collaborations, where my goal has mostly been working to make progress in the fields in policy and management, using tools in computer science as needed. Often what we need isn't quite there, and so then I will also work on computer science research that'll move it forward. It tends to be in the big data space of using existing data sets and doing lots of database studies. Some of the methodologies I've looked at is record linkage, which is how you combine all the different data sets in the appropriate way so you can actually run statistics. You can't run statistics until you have the data put together correctly. So I spend a lot of time trying to make sure that the data is getting put together correctly and how you should think about putting the data together so you can run statistics. I've done stuff in sequence analysis, which are things like if you have sets of diagnosis over time, trying to find general patterns in those and summarizing. And most recently, I guess, I'm co-leading an X-grant, large X-grant on campus, which involves 3 schools, 4 departments. It's got 3 aims, and aim 1 is with collaborations with Bobek in computer science, is more the developing the machine learning to predict hypertensive events so that you can take proactive actions as appropriate. But I guess I might have a little bit of a different perspective of the two previous speakers who talked a lot about how machine learning is statistics. I would say I agree statistics is a key part of it, but I tend to work on an end-to-end system that actually is everything. And I think statistics is in the middle, an algorithmic part, but if all you have is statistic, you don't really have a system that's usable. You have a paper to write. You have an interesting algorithm to talk about. So I tend to talk about all of those. And the reason I put it this way is in our project, AIM3, which some might say is not AI or machine learning, it's actually most of what AIM3 is. And the leads over there are in industrial systems engineering and psych, which is interviews with patients and providers. Because in order to actually take the algorithm out to have impact, you have to build systems that interact with people. And so AIM3 is really about what is the system design that's going to make it possible to take our algorithms out to the field to have impact. And then AIM2 is more of a simulation health economics model. And I collaborate with a health So I'm a computer scientist sitting in public health. So sometimes it's easier to collaborate with people in computer science. When we're writing grants that have to be cross, I'm like, hey, this is easy. I can cross with computer science. And then I'm writing grants and I collaborate a lot with health economists in my department, but we're in the same department, so we don't count. We're in the same field, apparently. So I think, just to have a flavor of these challenges, what is interdisciplinary research? What does it mean to collaborate? Where are you sitting? I decided early on after my PhD to sit on this side because I wanted to make progress and work on problems that would make progress in health rather than focusing on what's the next algorithm. I will develop algorithms as needed if I need it for solving my health problem, but I wanted to do that. So that's why I'm sitting on this end. But I often find myself, feeling more in line with people in computer science because that's my training and that's what I know. But I think there's a lot of exciting work these days and there's just a lot to do in this field. And it involves a lot of different fields. I think actually, developing algorithms and statistics, which actually even developing algorithms is beyond statistics. There's actually something called programming that's not statistics. Many statisticians do that well, but many statisticians do not do that well. And it's about, you did the math, now can you actually get your computer to do that thing? And that's a totally different thinking and learning that I think that's an important part of all of this. So I look forward to the talk today.
Okay, well, thanks for giving us your initial perspectives. So here are some distilled questions, and I'm going to kind of enlarge on these as well. But the topic of the panel is what makes us a cross-disciplinary project successful. If I look at these questions, I think a lot of them coming from the point of view, how do we actually get to that project in the first place, let alone make it a success? So, if you think of the first question, how can AI and health-oriented researchers get more information about the research interests of complementary faculty or related faculty to identify potential collaborators? So you've been successful. What did you find was a good way to do that? Or if you look back, if you think, oh, if only there had been X, Y, Z, that would have really, really helped me. Or maybe, in your roles in directing projects or labs, you've actually taken measures that have helped other people. So who'd like to go first?
So I can talk about this first. I agree with Kai-Chun's point that what you said, statistics is a big component in the AI research. And I don't think we are trying to say statistics is AI. It's not that. We are saying it's a big component. I was in computer science background, and I moved to statistics. So I understand and appreciate the value of both sides, the infrastructure, the hardware side of computer science, the framework of facilities, and also the programming implementation of the methods, as well as the importance of the method development in the theoretical end. So both sides are important. So I think for communication connection is that we need to understand each other, regardless whether it's computer science, statistics, or the health science, different departments. So make sure we are on the same page. And I appreciate also, I look forward to the collaboration with computer scientists. And I understand completely your point and agree with you 100%.
So I'm taking it from there. This is actually going too much, right? So if you cannot hear me, let me know. When he started these data science things here, so Nick started these things that all one day, whole day, every faculty will come from different direction who are interested in AI and health and give a 15 minutes presentation, just what you are doing. So there are two sections. One is foundational AI, another is health. You come, you can be anywhere. And I think AI is everywhere. AI cannot be statistics and computer science. I'm trying for a institute from last year. I told the basics of AI is how you integrate with human intelligence. You try to mimic human intelligence. And if you don't know philosophy, if you don't know brain scientist, AI doesn't work, frankly speaking. Just you cannot take AI and take a black box and put it somewhere. So if you start a whole day things, and if you say it's health and AI, so you can allow faculties to come from different departments, like different colleges, and tell what they're doing and how they're connected. Just a bigger version of what you are doing here, like Nilanjana. And it could be 2 days. We have so many people working so that you can get connected. Second step, what Nick did was making a big email list then, right? So whoever coming there, they're signing up, giving their information, and creating a platform where people can go and find out this website, all the strengths, what people are working, statistical AI, computing AI, getting them in the market, or application in health, different parts of health. Health is huge. Are you working in the insurance, big public health data, or you're working very experimental health data, or you're working on nutritional studies, right? Alicia is here, she's one of the world expert there. So those are the things we can create these platforms, and we can, then it's very easy. This is another AI, like another create AI platform where people can search Tamil folks, and whatever you are doing, you can search each other out, and we can work together.
I was going to say, I found, so in terms of just connections, the start of team science is to find the right composition of teams with complementary skills that are sort of focused on synergetic focuses. And it takes time and energy to do that. So I found the X grant mechanism we've had. I think we stopped it and moved on to other things. But the X grant, the two collaborations I've done that actually has a big component of this were both through the X grant. One was through the T3, where you had 3 people come together. The other one was the large X grant. But the collaboration that I guess in a way is the furthest from where I am is I also do stuff in AI governance. So Cason Smith is here. And it's, he's again in our department, he's a JD in our department, but we collaborate with, law professors at the law school. And all of those connections that I developed were through the X grant, where you kind of, I think what I'm saying is, you have to recognize team science takes extra energy and time, and you have to, as a person, be willing to do more than you are typically doing in your area with a narrow focus with the people that all talk the same language. So it's just recognizing that it will take more time and energy. That's you as a person, but it's also, if you're trying to facilitate this like TIMIDS is or A&M is, then institutions have to actually incentivize and allot for time and energy for these connections and communications to occur. Because what I have seen on the flip side is people calling things team science when, because of the lack of extra time needed to get the syncing done, it doesn't get done, and it's called team science, but it isn't. And that's because that extra time and energy needed isn't there. And so I think that's one of the key things about trying to do it in a way that you actually have synergies.
So there's actually a science to team science, right? I mean, there are whole seminars on how do you put effective teams together. And the CTSAs have been actually very focused on that because CTSAs are all about team science and advancing to applications to make cures for diseases. I think, and I totally agree, that it takes a lot of extra time. And let's face it, we're academicians. What brought us together? The possibility of getting a big grant, right? Come on, let's just put that right out there on the table. So usually the ways to get collaborators is to find some funding mechanism, build a bigger vision, and really get people who are passionate about a topic, who have very, very diverse expertise. And then what does that take? Well, that's like a Spanish-speaking person working with an English-speaking person and a Finnish-speaking person, right? I mean, our languages in all of our disciplines are very, very specific. So once you get that very transdisciplinary team, you have to establish a common language, right? So that the variables, when I say them as a surgeon, the statistician knows what that variable means. And you really have to be very pedantic about, we have to have a common language. Otherwise, the statistician and the machine learning people think I'm saying one thing when I'm really trying to guide them somewhere else. That's what really takes the time, is getting that very, very common language, making sure that when I say something, you understand me, and when you say something, I understand you, so then we can move forward and get to, you know, the goal of our project.
I would say one key element for success in these large teams is curiosity. We talk about money. We talk about going after grants. But if we focus on the money, we forget about the rest. You have to find topics that you are curious about. That, I think, is the only way. If you don't have that, no amount of money is going to make you happy and therefore make you contribute.
So Paul and Xiaoning, you in your answers, you talked about team science, and you also talked about, in the context of that X grant, you made that effort to reach out and develop that understanding. So do you think that that's something which could be, you know, more strongly supported, or there could be resources for that? Or, you know, in your case, Xiaoning, did you feel that was kind of within the remit or the expectations of the program, the programmatic funding to do that? Or was that just something you did because that's something you think is important?
So I was on the X grants, I guess, I was on the planning committee. So I was involved with the whole process for a long time. And so I guess from the committee meetings, that was the goal. So we spent, this was like faculty from all schools on campus together, coming together to say, what would it take to do team science? And we had many meetings to set up design the X grant mechanism in such a way we could facilitate it. I would say one of the difficult things in that process was, you know, there's a lot of places for seed grants for team science. That's in a way, money may be the easier part, because you can find money, and we know there's seed grant mechanisms, and we can say, write it. What I think personally in that planning process I found hard was the evaluation. So, you know, we had everybody on campus, lots of teams submitting grants, and then we had to come up with a way to review it in an objective way. Number one, this isn't that big a place. So it was the same with me, right? There was a lot of conflict of interest during the review. So you try to make sure that, you know, you do something about it, but there's that. But beyond that, expertise is a problem, because in order to evaluate of the 5 grants that are all talking about, you know, one, because there was a lot of them that were similar, to differentiate which one was the good one, you need expertise. But this is, you know, within A&M's review process, all of the experts wrote those grants. So if you do conflict of interest and you took them out, who's there to review who's an expert of this thing, right? So I found that when I was going through that experience of trying to facilitate team science, that the evaluation of those things, you know, was quite hard to do. And we did what we could, and we did stuff. But then the other thing that came out of that process was there are fields of team science that are more advanced and matured than other fields. So for example, in the initial years of those grants, almost all of the grants that made it to the very top and got funded were in certain fields that were very advanced in team science, like biomedical. So it's like you have a department of biomedical that is, all they do is team science. So they've had practice doing that. They know how to write grants that is a team science grant, versus if you had 2 fields who've never done it together, meeting together to write the grant. It's just the team science nature of the grant is not as mature. So all of these were very difficult because there are certain fields that are good at team science. In a way, I think of bioinformatics as one of those, where it's now a field of its own, and you go to any bioinformatics department and it's got interdisciplinary people in it. So the language they speak is an interdisciplinary, right? So then do you consider that now that's no longer something we need to facilitate with extra energy because they're all settled? We go, excluding those people that are all mature, we're going to do this. So I think these are things that you need to think about as we do things, if we're doing things across campus.
I want to thank actually A&M for seed funding. I think they are very, very helpful. One success story is I didn't know anything about material science, and I hated chemistry all through my life. So we got the money, AI and material science, and we got the seed grant, it started. Last year, we were the finalists. There are only 2 universities, Nick, and you guys know very well, with $30 million center on AI Institute. We missed it out, but we went all the way, beating every other university at the end of the day. University of Washington got. They're also outstanding, but it doesn't diminish our pay because all people from chemistry, from material science, from statistics, from computer science, we work together to write the grant. And the seed started in the seed fund. Again, we got some funds this year from VPR. They are very, very useful because at the end of the day, we are all busy. But when the students or postdocs start running around, then we start running the language, learning the language through them. Like, we are in 10, 12 projects. So I can tell you they are very, 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 very useful. And I'm confident within 2-3 years, we'll get a big institute on science, what invested on us. So that's our responsibility to get.
So maybe at this point, we can sort of move on to section 3, since people have been talking about seed funding. So, like any preliminary, activity, some things succeed and some things don't, and that's part of research. Well, or is it just part of research? I mean, if we think about, how, if in addition to just making the awards, do you think there's anything that could be done to increase the success rate or increase the outcomes, in terms of transitioning seed grant activity to something else? Is there any support that can be done to kind of increase the success rate? Or turn it around, if the seed grant activities you've been involved in, which didn't pan out, was there something systemic in that, or was it just, well, the research wasn't sufficiently aligned? Get your insights.
I've been on X grants, and that's been a great mechanism. The one thing that I learned is that if you try to build, if you use seed funding to build these very large teams with people from all colleges, the efforts get diluted. And so I think there is a Goldilocks zone for, areas that can gel quickly. That needs to be considered. If we just look at course measures of cross-disciplinarity, how many colleges are in, that's not going to be a good measure. And I think because of the necessity of us being both proposers and reviewers, that I think that was one of the measures that was used. And some like you said, some disciplines are far more advanced in cross-disciplinary research than others. And so how do you find that? How do you find those disciplines or regions or problems that are prime for quick collaborative work, and then build upon those, as opposed to, throwing a computer scientist, a statistician, a clinician, and see what comes out and sticks. So more targeted, more focused, smaller teams, and build incrementally, as opposed to trying to build one large team all of a sudden.
Yeah, I think I wanted to follow up on that because I had this. So I think a seed grant mechanism, and the first thing I wanted to say is whether you get funding or not. So I've written many seed grants. Many of them didn't get funded. Some of them did get funded. But to me, honestly, yes, if it gets funded, you can get further along in that progress. But the process of writing the seed grant is actually, I think, the biggest thing for making this going, in terms of when you have a seed grant mechanism, it forces you to talk, build a common language to write the grant. Now, I think all of us who've written grants know there are times when you just put a grant together, it took a day and it's out. Whether it's good or not is a secondary question. And then there are grants that you put a lot of energy into, and that's the same for team science. You can spend months talking to each other to write the one grant, or you can spend a week getting signatures after you wrote the grants, right? There's different ways to do this, and it depends on the situation, what you do. But just the start, even if it's the latter, which is not something that's great, but even if it's the latter and you spent the time to get the signatures and they've started to look at it, is not likely to get funded, but that's the start of it. Because then you start to see, oh, there's something here, and then you're gonna look for the next mechanism. None of this is you do it once, it goes away. So I think the important thing about the seed grant mechanism is to start to build a team, bring people together to talk to each other, regardless of whether it gets funding or not. Even if it got funded, typically seed grants are so small, you can't get very far. So this is what goes to the second thing I was gonna say. I've seen a lot, seed grants are everywhere for team science. Everybody, team science is great, seed grant is it. What I haven't seen that I think is needed to do what you were saying, you have to take to the next step. So it's, I don't know what it's called, but it might be of the seed grants, the thing that really sees, like, we all try things. We tried it. Oh, I guess there's not much promise. You let it go. But of the different seed grant activities that occurred, it ought to be, there are some that actually is starting to be something more mature and you can see promise. And then at that point, you want to, that's the one, those are the projects. I've done many. I've given up on money after the first seed grant. I'm like, oh, I see there's no promise. That's research. I learned this, there's no promise. I move on, right? But then of the many activities I've done, I've seen this one has a lot of promise. I can see we have a good team. I can see we want to take it to the next step. But the gap between the seed grant, like a internal seed grant, to the get the big team science grant from NSF, NIH is so huge that now I have something. I figured out with the seed grant that I have something, but we're not at the point where we can compete nationally with all the other people who's been doing this forever. So there's nothing in the middle that is allowing me to actually mature the thing that I started with a seed grant to move to that national level. So what I see typically is you have people who are already in the national playing field. It's the same school, same player, and you don't have new ideas, new people coming in. How you normally, this is my mind, how you normally branch new things is you go to the teams that already exist that have NIH funding, you get to know them, you sell them their idea, your idea, and they give you a part of their money to do that, and then you get to a certain mature level. So I think if you can find mechanisms that actually will take not the seed grant, but to the next level, where there is now a lot more rigor in looking at it. So seed grants are supposed to be this way. It's supposed to be very risky. Half of it's that, but that's research. That's good research. It's just after that, you want to benefit from what you learned, which means take the ones that have more promise to the next level. That is, I think, more lacking in support infrastructure.
To follow up on that, it's like the valley of death for any innovation or any project, right? You got this great thing and then you have the valley of death. So I would suggest, rather than going from seed grant to major NIH NSF center, you look for subgroups of your team. I'm obviously much more familiar with NIH and have had a lot of different grants and different mechanisms there. There's RO3s, which are $50,000 a year for 2 years. There's R21s, which are basically $250,000 over a 2-year period of time. There's career development grants, right? So rather than going from that, next big step, you take parts and pieces of your team, parts and pieces of your idea, get them funded at smaller levels, get manuscripts written together, proof of concept, trainees getting into K awards or postdoctoral fellowships or all of that good stuff. And you build it that way to try to avoid that valley of death that happens to so many things. And I'm sure NSF also has kind of similar, smaller grants that could be used to make you then competitive with the big boys.
I completely agree with you. Going from a seed funding 100,000 to expecting that group to put together an AI institute or an ERC is very problematic. So start small, understand the different mechanisms at NIH, at NSF, and build slowly. Once you have enough critical mass in different areas, then you can try to integrate them into a larger AI institute or center.
Actually, there are some bigger seed grants also that, we got something almost $500,000. And we have people from maths, people from 5-6 people, very much targeted. I can tell you about our institute proposal. That institute proposal from there, at least we wrote smaller 9 or 10 proposals from there. So we are hitting everywhere. We never write one grant proposal in life, but why I'm saying, I just came out from a NIH study section on these institutes. A big question they ask, do these investigators ever worked before? That's a crucial question. We could have outstanding Nobel winners, but get one from here, one from there, and try to write a proposal. They're never going to give you money. They say it's an outstanding proposal, but these seed grants are helping us. It's showing us some initial results. So I'm very much pro towards these seed grants, whatever it's 100K, 50K, or $500,000, it takes you all the way. I'm delighted about this venture.
Yes. So this is quite interesting, and thank you very much for all your thoughtful comments. So first, I'm very delighted to hear that the X in the grant, the T3, the TPT grants are really very useful to you faculty. So that's great. That's very encouraging. So to your question about creating different levels and different opportunities for internal funding program. Actually, that's essentially what we have been talking about. Our team, we've been having that conversation this year, and you're going to see a little bit of that in our TPT, revised TPT RFP that's probably going to be released next month. So in that, we identified different levels that may address some of the things that you've talked about. So we address the classic seed funding program that would maybe 2 or more faculty can just come together and use that to collect data. Okay, so that's classic, seed funding. It's for data collection. That's one category. Then there's a category for planning grants, whereby teams who already have those like seed funding and they've used it to collect data can then come together. So you can have multiple teams now coming together to form a bigger team to maybe go after a big opportunity, and they can use the funds to mine their data. So think about, let's say you have 2 or 3 teams that already have data and they've been working together. Now they want to go after maybe an AI institute, but that's probably too big. But you need multiple teams. If you're going after an AI institute, it's not only 2 people. You need multiple teams. So we have planning grants for that. We also have a new funding category that we call grants on edge. So, or we call it good to great. So think about the success rate of most of our funding programs, 10 to 15% maximum. You can have a very good proposal that you send to an agency and it gets very good reviews, but it's not funded. There's probably 1 or 2 things that you need to do to polish it, to take it to the next step. So we have a new program that we're unveiling. We call it Grants on Edge, or Good to Great. So taking your proposal from good to great next year. So that can help actually, because what you don't want is you don't want proposals that are already almost there, but because they don't have funding to continue to, advance that, then they are not able to resubmit or compete. So we have another program that we are going to unveil to help those who have already submitted their proposals to agencies, but they need a little bit of funds to take it to the next level. So we're thinking about all of this. So if you have additional thoughts on how we can, modify our internal funding program to meet your needs, please let us know, okay?
So we had a very successful program at UT Health San Antonio called Grant Seekers, and it did exactly that. Even people before they put in their grant, and there was a guy named Sunil Ahuja who ran it. And so obviously Sunil wasn't an expert in everything that people wanted to do. So he would even bring in external reviewers, usually virtually. And so we had career development grants, we had our grants, we had, our CTSA, we put it through there. And so then the idea is even before, or if you've put the grant in, they look at the specific games and they beat on those specific games. And then the other thing is if you have a summary statement or a response to the reviewers, you come back or take your grant there. So some type of a program so that you get all the comments and the red ink on your proposal from here rather than at study section works really well.
If you can give, I'd like to throw in the remaining time, I'd like to throw it out to comments from there. But if you have something very, very quick you'd like to follow up on, let us know.
Okay, in 30 seconds,
Yeah.
I can talk about two things. Regarding the systematic inhibiting factors, I'm a representative in School of Public Health in the Council for Principal Investigators. I observed two things. I think it's not from the university level, but could be from the school level or the departmental level. So one thing is for seedling grant or the external grant, which is matched within the university, I think across different schools, there could be different policies regarding the spending of those funds. In some of the school, using those grants to block the faculty work time or the summer pay is not possible. Well, in other schools, it's possible. And same for faculty joint appointment. In my school specifically, if we have joint appointment, I see the regulation is that we cannot use the external fund to block the regular work time to pay the salary. So I think in other schools, I found it's possible. So I see this discrepancy between different schools regarding the use of the fund, and which it could be which creates a barrier for the faculty members to better utilize the fund. For example, in some of the school, maybe we get the fund, but we are not able to fully use it. And so I think if the university there could be some policy or the faculty could have someone to talk to, it's gonna be very helpful.
Okay, thank you. So are there any questions from the audience that would like to pose to the panel at this point? Okay, well, if not, we'll the one question. Sorry, what's the one? Right, okay. So, yeah, the question we didn't answer is kind of related. How can AI-oriented researchers learn about cutting-edge problems in the health domain? I think I'm going to rephrase that. What do you think are the cutting-edge problems in the health domain that you hope that AI can can advance in solving?
How many hours do you have?
Right.
Electronic health records are horrible. They really don't help the clinician. They are basically, and the data in them is often false, right? Because they're billing records. They really are not designed for healthcare, right? And there have been big initiatives, right? As a vascular surgeon, I want to know something different than a geriatrician versus something else. So something that actually would come up and bring all the studies that I would care about that are relevant so that I'm not spending an hour on your electronic health record trying to figure you out as a patient would be absolutely amazing. And I mean, the electronic health record has been like a huge time suck and actually is very much contributed to the burnout of clinicians. Now we're answering emails to patients. Now every patient can go through a portal and read a note and they don't understand half of the jargon in the note, and you get an email because the patient read the note and now they think they're dying because there's a word they don't recognize, right? So getting data together so that a clinician can spend time focusing on you, the patient, and not all the extraneous stuff would be critical. Coming up with things that are sensors, but oh my gosh, do you really want the doc looking at the sensor data? No, you're going to have to come up with the ways to make that data useful and meaningful, and how we do that. And I do like what you talked about, the black box, right? If you have a black box and you're making widgets and you're 90% off, okay, but do you want to be, 10%, if 90%, great. Do you want me to be 10% off with your healthcare? No, you don't. So really coming up with ways to decode the black box so that we understand what inputs are looking at, so that we can then design the next step and make it even better. And then I've also talked to Nick about this. I don't think there's an AI solution. It's not going to be machine learning or computer vision or this. It's going to be triangulation of a lot of technologies, because all of them will only get you to a certain place. But if you triangulate, then 80% in one is offset by, the 80% in the other, and we can get to a lot better solution.
Okay, 30 seconds on one cutting edge problem.
Oh, I don't have one cutting edge problem.
I can take one. Is practitioners using AI as a black box is very, very difficult, because health data is much more complex. They're too much on correlation, but the actual thing you want to learn is causality, something called. If a doctor giving a treatment, what's going to happen? What causes that? That's you're asking, which you're not observing in the data. That you have to be very careful. Correlation and causality is not same.
Okay, Hydro, 30 seconds on your cutting edge problem.
Yeah, I think for me, in a more shorter term, I like your, I think the idea of summarizing is really good to help with the inundation of data. That feels to me like a more longer term. So if it's, for me, the more medium term thing is working on things related to chronic disease, where you're building predictive models so that you are actually telling the different people, providers, nurses, doctors, patients, things that you can do because something is coming down the pike that you can do. So working on that, building a predictive model that tells other people that needs to take action, what are potential actions to take to make, chronic disease management better seems a more medium-sized problem.
Last call on 30-second cutting edge problems. Okay. Well, in that case, thank you very much. I think it's been a great panel. And I think your discussions, your comments have led to things, in particular interaction with Henry, that I think have a chance to make a difference.
Small technical questions can go. So I'll now introduce the chair for the past spotlight presentation on health and medicine. So our chair is going to be Alicia, and she is a distinguished professor and president's chair in statistics in Iowa State. She is also the director of the Center for Statistics and Application in Forensic Evidence. And she is in Texas A&M because she is the Hegler Fellow of 2023 to 2024. And one thing is that she is an elected fellow of National Academy of Medicine, and for her work, the way we analyze dietary data today is being done. So please welcome Alicia.
Okay, thank you so much. I'm enjoying my stay at Texas A&M greatly, I have to say. So this, we'll start this with, let me see. Sorry? Yes, with Professor Jason Moats, who is the director of the USA Center for Rural Public Health Preparedness. Thank you.
Thank you.
15 minutes and then I'll have the hook.
Okay, that's good because I need it. I talk a lot. Howdy. How's everybody doing? I apologize. I haven't been able to be here with you all today, all day, but I'm running between conferences literally. But I appreciate the opportunity to talk to you a little bit about my favorite topic, which is disaster response. And I know some of you are involved in this. And so we look at how can we integrate technology? My background is really different. I did not have the usual course to get into the professor. I ended up, I spent 21 years working at TEEX, the Texas A&M Engineering Extension Service, where we did a lot of training for emergency responders across the world. So just to give you an idea, TEEX trains about 220,000 people annually. That is online, that is face-to-face, that is mobile training, that's training we bring here. And if you ever notice the smoke clouds that come up over by the airport, that's TEEX, you know, and they're doing this training. So some of the people we train are those pre-hospital emergency responders, emergency managers who are doing the planning, who are doing the recovery efforts after a disaster hits, as well as the firefighters, the police officers, the public works folks. And so all of this fits into areas where we can bring in technology. Digital twins are a really important piece of what we do, so we can model and look and how we bring things together. So I've got 15 minutes, and as I said, I'm pretty long-winded. So a picture's worth 1,000 words. But I want to talk to you just briefly about the current conditions that our emergency responders are working at. First of all, we know, and there's clear evidence that disasters, the magnitude of disasters is getting more and more complex. So when we sit around and we talk about, you know, oh yeah, there's a hurricane that has come in, we're seeing not more hurricanes, but more intense hurricanes. And if you were here for Hurricane Harvey, you'd kind of know what we were talking about. You know, 36 inches here in Bryan College Station over the period of about 14 hours. Down in Houston, 58 inches. So that's a lot of water. The other thing that has been noted is when a house burns, 25 years ago, when a house would burn, it would, a room, we could light it off and it would probably be fully involved in about 5 to 10 minutes. Now we're talking 30 seconds. So, and it's because of the materials we're using, it's because of the construction we're using and things like that. So these things get a lot more difficult to deal with. They move faster. We don't have as much time for decision making and things like that. In addition, the work is stressful. So if you're an emergency medical technician or a paramedic riding on an ambulance, you are seeing people day after day, hour after hour on the worst day of their life. And that compounds, you can imagine how that compounds over a 25-year career. And you're lucky if you make it to 25 years because picking up people, you end up blowing out shoulders, backs, knees, and things like that. So it's really tough, both physically and mentally on the responder. The developing the public safety workforce is also much more complex because, first of all, there was this little thing, I don't know if you all heard about it, the global pandemic. Yeah, I know it was just a blip, okay? But the reality is we have seen a pretty significant exodus of people who were in the career and we expected to be in the medical field, in the pre-hospital healthcare field for a while. And now they made an early exit. And we're not able to bring people in at the volumes we were before. So we've got a little bit of a problem with the workforce. And oh, by the way, you can't just simply bless somebody and say, hey, welcome to the back of an ambulance, because that's not the way it works. So we have that going on. And then the health and wellness is now forefront, where before it was, we are here to save you. We're going to do everything we can. You know, if we have to give our life to save you, we're going to do that. Now there's, no, that's the wrong approach. We have to take care of ourselves so we can be there to save multiple people, not just one. So, like I said, a picture's worth 1,000 words. When we talk about potential AI applications and disasters, and this is generic, but it's also specific to healthcare and specific, especially outside the hospital. We look at it in emergency management from a planning perspective. So think about the next pandemic. We just had a meeting with Scowcroft Institute or at the Bush School today, and we're talking about what is that next pandemic going to look like? Now, what if that next pandemic isn't human, but it's animal? Think about that just for a moment. How can we even figure this out? How can we look? What supplies do we need? To do it manually, to do it with a working group, it would take about a year to develop a plan. But with AI, we know that we can develop plans rather quickly. In fact, ChatGPT and those other large language model AI can give us the opportunity to really build the guts of the plant. Still needs to be validated, but in a matter of minutes. So it's really helpful in at least giving us a start. Another thing is health monitoring and predictive analytics. Imagine this, you have a disaster in before you have a disaster in your community, I have all of the data on electrical usage and your visits to Walgreens. You're like, okay, I can see some of you going, what? But I can sit down and tell what some of your likely medical problems are that you are dealing with at home. So maybe you're on a respirator, maybe you're given nebulizer treatments every day. Now, disaster rolls in, you lose electricity. That changes my priorities of how I'm going to do that, how I'm going to get to you, what I'm going to get to you, where I'm going to put you in a shelter, and things like that. And so all of that, AI provides us an opportunity to do that analysis very quickly and make some very quick decisions about how we're going to take care of people. On the response side, I'm just going to skip through some of these. Surveillance is a big deal. We talked about using AI in uncrewed aerial systems, so drones and AI to be able to do stitching together to look at where people were flowing, how people were moving, and things like that. If you have ever tried to stitch a picture together, it's a tough thing. So having AI that can help us and line those things up are really important. Also to do the analysis, because there are things that our eyes won't see that the algorithms can help pull in. And that's not just visual, but that's also looking at, other types of feedback. One of the really cool things I would love to see us be able to develop is using a system. And so bear with me. I don't have this picture on the slide, but bear with me, where we're using augmented reality in rural hospitals, okay, where that clinician that's sitting in the rural hospital has to go through a advanced cardiac life support algorithm. Okay, so this algorithm's pretty intense. Okay, there's a lot of pieces to it, and depending on what you find at certain decision points will depend on what you do. So if you haven't done it in a while, or you're not really experienced in doing it, wouldn't it be great if we had a virtual coach that's doing the analysis, that's feeding information into your ear? Now, there's a way to go on that, and I'll cover that in a minute. But imagine this, or imagine an AI. Have y'all ever heard of West Texas, the West Fertilizer Plant explosion in 2013? Okay, 265 people injured, laying on a football field. Okay, that's where they brought all the casualties. 265 people that were there. All of them had to be talked to, identified, triaged, so that we can make decisions about who went to the hospital first. Wouldn't it be great if we had little devices that we could simply put on somebody and say, okay, they have a good heart rate, it's strong, their core temperature is good, they have a good respiration rate, okay, and they're conscious. And the person laying next to them, maybe they don't have a great heart rate, maybe they have something going on and they're not. So we can make a decision before we even get the stretcher to them. And so we're directing people. Yes, okay, thank you. So on the clinical side, personalized medicine. So I had the opportunity to work and talk to the Undersecretary for Homeland Security for Science and Technology. And one of the things that became, he is an AI guy through and through. And what he told us was, you know, that surge that we depend on for people is no more. So we have to look at other means to do this. And AI becomes some of that piece that helps make up for losing the surge of people. And so what we talked about and what he has done extensive research on is adaptive medicine. Okay, that is specifically to the person, but he's also done it on using AI for rapid drug development and discovery. So supply chain becomes really important as well. If you don't have supplies, you don't have bandages and beans, people suffer. So we need to make sure and look at how we can position things in a disaster. And then the recovery and the damage assessment and things like that are all really important analysis that takes a long time that we can speed up. So these things don't come without their challenges. So a big issue that comes out is cost. We have to figure out ways to lower it. I love the rural communities in the state of Texas and throughout the nation. I grew up in one, okay? And the big deal is we really can't afford to give them a $300,000 computer system. We need to give them a $300 computer system, and we know that there are some communities can't afford that. So we got to figure out how to lower that cost. Limited accessibility, so the computers can't talk. Sometimes they don't even have computers, they're working off iPads or iPhones. So how do we build that and make it so that on the edge, they are able to access it no matter what device they've got? Interoperability is a big deal. How do I transfer patient data from one system to another? Because that's what's going to happen. We're going to be moving people away from the disaster. User acceptance and trust is really important. First of all, do you trust AI to make diagnostic decisions about you? Yeah, didn't think so. How do we do that? How do we build that in? And then how do we get the end users to use it? How do we get them to see that it helps them do their job better? How do we get them to see that they can use it? And how do we get them to see that the juice is worth the squeeze? And what I mean by that is that the time and effort and sweat and blood and tears that they put into it pays off in the end. So, and then of course, training. I have technology for technology's sake. We don't want to do that just to say we're using the coolest bells and whistles, especially if it's just a loud clanging gong that means nothing. So that's 15 minutes. I'm Jason Moats. Thank you.
Good. You had like 3 minutes left.
See? That's a first. Oh.
Thank you. One quick question, if there is any, right? No? Okay, very quick.
Jason, a great talk, a big vision. So do you have any good example of how
use AI to train for the local?
That triage model that I mentioned. We actually did some work on an NSF project. It was Nilanjana Mehta, myself, and a team from Virginia Tech, Clemson, and University of Florida, who I think you know. And so we built some small adaptive AI pieces that would take the training and adapt it to the user, to the trainees' learning styles, to what they were missing, to what they were getting. We also, that triage model, we were building to do what I said it would do, which is actually monitor the patient autonomously and make decisions about how that patient fell in their level of criticality.
Thank you. Thank you. Okay, so the rest of the questions, save them for the end. Our next speaker is Cason Schmit. Cason Schmit is director of the program in health law and policy and assistant professor in the Department of Health Policy and Management. Thank you.
Thank you very much. Very excited to be here and have an opportunity to talk and share a little bit about my work. But I'm really interested to hear about the work that you're doing, particularly if there's some opportunities here. So structured a lot of my talk talking about not just the work that I'm doing right now, but perhaps, you know, how there might be some synergies with what I do and help you all see if there are any connections that we might work together. I'm the lawyer, right? So I'm a little bit different than the traditional academics. I also don't know how to use technology.
Okay.
All right, here we go. So I'm a lawyer, and my background is not necessarily in academics, but in government. I started out at the CDC where I worked on using law as a tool to promote public health. And my primary focus there is developing legal tools to assist the use of data, broadly speaking, not just clinical data, but data to promote population health. Currently, one thing that's relevant that I'm doing right now is I sit on the IEEE Standards Committee for AI ethics. And so we are actively working on developing standards for the ethical use of AI. My current research areas, one overarching theme of my research is I look at law as a determinant of health. The governance of various things, and in particular AI, is going to affect our health as a population. And so it's a very difficult problem that needs very creative people to think about it. I look at data, I look at law, I look at ethics. I am very interested in the incongruence between the legal rules and the legal governance frameworks for data processing, and public health ethics. We like to think that what's legal is ethical, but not everything that's ethical is legal, and not everything that's legal is ethical. And so that's a very overarching theme of my research interests. I do a lot of work in surveillance, and particularly public health surveillance, and how the laws affect the capacity to do that surveillance. And of course, I'm also very interested in technology governance and health. To give you an example of that, one of my more recent publications was in Science, proposing a new governance framework for artificial intelligence. Governing artificial intelligence is going to be a really, really challenging thing. Technology moves fast, law moves slow, right? There's the whole concept of the AI effect, which something is artificial intelligence until it becomes commonplace, and then it's just computation, right? Defining AI is a problem because you need to define something to regulate it, right? And so having an emerging technology that's changing every moment makes it a very vexing regulatory target. So we can't use existing regulatory tools. We need to come up with a new way that can be agile and adapt to changing contexts, changing applications, and emerging risks and opportunities as well. So this was an idea. Also, it was unfunded, right? Seed funding, right? Good ideas come from some of the craziest ideas and some of the craziest ideas are the ones that need a little bit of help getting off the ground. Enough about that. Let me talk about some of my ongoing works. There were a number of speakers in our very first panel that mentioned that AI requires data, right? And in the context of public health, our data systems are way out of date. Fortunately, perhaps one of the silver linings of the pandemic was that Congress realized this and provided a substantial amount of funding to modernize public health data infrastructures. I'm currently working with CDC right now to modernize the policy framework for those new data infrastructures, looking at the policy barriers and opportunities so that we can modernize the public health data, so perhaps we have greater opportunity to leverage AI to do the very types of things that Jason Moats was just talking about, right? We need to have a supportive policy framework or else we just can't get it done. Raise your hand if you've ever worked with data or tried to get data and somebody has said, sorry, we can't give you that data, the cell sizes are too small, right? That's kind of the thing that I'm talking about here. And that's also the subject of that National Academies grant at the bottom. One of the problems with our governance framework for population data is it rests on bioethics, which is a much more intimate ethical framework that deals with personal relationships between clinicians and patients or researchers and their research subjects. When we're dealing with large database studies, we don't have those personal relationships. And so the traditional protective measures like consent and the defaults that come along with that, like suppressing small sample sizes, manifest themselves into barriers to getting data that we need to do socially beneficial things with it. What does this mean for vulnerable communities? Those small sample sizes, they're often invisible, right? In 2022, there was a report by the Urban Indian Health Institute that basically accused the entire US public health system of data genocide, where the lack of access to needed data was posing an existential threat to their communities because they didn't have the tool that they needed to understand the health risks facing them. I could go on about that. That's another area of my work, but I want to move on. This project specifically is looking at syndromic surveillance and how we can better align the policy structure that decides what gets seen, who gets seen, better aligns with the needs and the comfort and the value of those vulnerable communities that are most at risk. The awesome thing about both of these opportunities is they are exceptionally well timed for policy impact. CDC is modernizing these policies, and they are very, very open to the types of changes that we need to do cool things in AI with these data. And so that's at the forefront of my mind as I'm working on both of these projects, is what sort of recommendations are going to lead us to that next age of artificial intelligence, machine learning, where we can really take these somewhat sophisticated systems in method, but not in technology, and move them to the next level. All these images are AI generated, so there's a little craziness. Like, I don't know if you can notice this. This is what I told them that my this is my intersection to research image. I don't know what DS ibis lose is. So why am I in public health policy interested in AI, right? One, I think there's a huge opportunity to leverage public health policy innovations to improve AI governance. And one of the reasons for that is public health has long wrestled with this balance, this competing tensions between collective interests and individual interests. And those are the same types of interests that are vexing policymakers in the realm of AI, particularly in the realm of privacy, right? And public health has long wrestled with this. And so I'm really excited about the opportunity to bring some of the public health policy innovations and interventions into AI governance. I also see enormous opportunity for AI as a tool to support public health practice. Supporting surveillance, Jason was just talking about that, particularly syndromic surveillance and wastewater surveillance, I think are really promising applications. Precision public health, learning health systems, optimized resource allocations. Jason did a great job covering all those. I'm not going to touch them. I do have a funding target that I'm looking at. It's building on that framework I was just talking about that we published in Science in terms of biomedical context in the form of an NIH grant. If that excites anybody, love to talk more. If anything that I've said, oh, I'm going to be early, don't you even worry. if anything that I said interests you about the type of work, or you seeing value in having somebody who's policy focused, a lawyer at the intersection of law, technology, and ethics, I am very interested in talking with you more about some of your ideas. I'm very interested in AI governance. I'm very interested in AI applications and the ethical considerations that come with those AI applications. And I am very interested in AI uses by governmental authorities, particularly on the public health side. Basically, if you have an LC component or an LC component, would it help you enhance your research idea? I'd be really interested in talk with you more about that. I'm really excited about this area and doing more. I've got two awesome postdocs, both legally trained with good ethics backgrounds as well. One of them also sits on the IEEE Ethics Standards Committee. And I've got great relationships with some of the data governance folks in federal agencies, specifically CDC and HHS, as well as a handful of state agencies. So there's good opportunities to bring those sorts of insights and projects as well. So did I just fly through that? I think I flew through that.
Excellent.
So yeah, happy to talk more about anything and everything.
Thank you so much. What? It's okay. Thank you. All right. Our next speaker, Lu Tang. There she is. Professor Lu Tang is a professor in the Department of Communication and Journalism. Oh, there it is. Okay. Looking forward. There we go.
Okay. Well, speaking right after a lawyer is a bit scary. Make sure I say everything right. So my name is Lu Tan. I am a professor of health communication in the Department of Communication and Journalism. I'm also the director of the Data Justice Lab, which is one of the thematic labs funded by TAMIS. So yeah, so I am very thankful for this opportunity to come here to share with you some of the work that I am doing and we are doing in the lab. Hopefully we see some common interest. So in general, my research looks at emergent technologies and how it can be applied for health promotion. So, and within the Data Justice Lab, we are interested in anything social and ethical implications and applications of data science, of AI. And in fact, my collaborator, Wayong Siegel is here. Dr. Siegel and I are right now working on a NIH grant where we're building a VR educational module to teach medical AI researchers about AI ethics and bioethics and all those nice things that were just talked about. But today I am going to mainly talk to you about leveraging chatbot or large language model for health promotion. Okay. So you're familiar with chatbot or annoying, customer service thing that they try to replace people with. But in healthcare, in health and medicine, chatbot can be potentially quite useful. It's been there for a while. So some recent analysis shown that it can be used in screening, diagnoses, for symptom monitoring, and for the promotion of behavioral change. So that third thing is what I'm most interested in. And of course, there are a lot of advantages associated with chatbots, like always available, personalized communication instead of just a web page for people to read. It's interactive, you can ask questions, and also chatbot can provide behavioral change support and mental health support that are individualized. Okay.
And there has been the old and new chatbot. The old chatbot is the traditional conversation agent. It's rule-based response to certain questions. You have an extensive script of how to answer different questions, right? If they ask this, and you go to this, and then it has limited understanding. It can deal with simple tasks, and it just has a script, so it doesn't learn, and there is less personalization. So basically, if you ask the same question, you pretty much get the same answer. So this has been the chatbot that a lot of us in this field has been working with in the past. But with the rise of large language model, suddenly the AI-based chatbot becomes a possibility. The threshold just gets a lot lower for a lot of us to work with. AI-based chatbot, has contextual understanding of what's going on instead of a mechanic answering of questions. It's can perform adaptive learning, can achieve complex tasks. There's more personalization, and it only even has predictive capabilities. That is, it can predict what you might ask, what you might need. So, so I've been playing with both. So, for instance, this is a HPV vaccine conversation agent project that I'm working on. It's currently funded by CPRIT. So, we're familiar with HPV vaccine and HPV and how it can be, can be prevented with the vaccination. The HPV vaccination rate is still quite low, 33% in Texas, lower than nationwide, 43%. And research has shown that strong provider recommendations are a major influence on uptake, with 95% acceptance rate with counseling. So that means if our doctors strongly recommend it, then the patients are very likely to get it. However, doctors are busy, and there's limited time and inconsistency in where doctors make strong recommendations. And then there's a lot of hesitancy, and with the anti-vaccine movement, so a lot of the conspiracy theory out there, there is a lot of challenges in increasing the vaccination rate. So, so we're building a old-fashioned chatbot. That's when what we do when we wrote the grant before ChatGPT and large language models. So we use psychological and behavioral theories to create a script. And then we tailor language for young adults. So the goal is to put this chatbot in the waiting room of pediatricians and doctors. And so when you're waiting, because they always keep us wait because they're busy people, and then you can talk to a bot. I would think, a teenager or young people will be quite interested in it and mess with it a little bit. We will change adapt the tone, and we also incorporate testimonies of survivors of HPV cancer patients, and then plus all the factual informations. We build this into a very extensive script. The goal, so to promote HPV vaccine and knowledge and vaccination intention. So, so these are some of the theoretical psychological constructs that we are going to address that research has shown to promote the adoption of a health behavior, like decrease perceived barriers, telling people it's easy to get, it's available, tell them how to get it. Perceived severity to increase, for instance, perceived severity to tell them how serious, the consequence of HPV, some of the HPV related, warts and cancer can be. Change perceived susceptibility, telling people, we're all susceptible, etc. and etc. So the goal is to, create this chatbot that is driven by a series of psychology and behavior to promote not only the knowledge, but also positive attitude, but also get people to actually engage in this behavior. So we did some preliminary work with our student, or undergrad student here. We tested the usability of the chatbot. It was okay. And then you can see that different types of people see it differently. And then we also briefly looked at the improvement of vaccine attitude. And well, you can see on like risk denial, perceived harm, perceived uncertainty, the chatbot was actually able to change people's attitude towards the correct direction. So that is one of the secret projects. And on the one side, we care about how to build the chatbot, how to put in the right information to have the good technical feature to make it more human-like, personable to talk to, easy to deal with. On the other hand, we can also study the user behavior. So different users interact with chatbot differently. There's algorithmic preference or aversion. Sometimes we want to listen to the computer. Sometimes we don't want to listen to the computer in this case. Or media literacy, health literacy, all these different factors influence how users might use the chatbot differently. So another project we just got a seed grant on is using chatbot for college student mental health support. Yeah, so there's a mental health crisis among young people, youth in the United States. Well, we're all college professors or students here, so we know that. Mental illness, so this is a general issue. And for mental illness, the mental illness stigma would prevent people from seeking help. In addition, research has shown that ethnic minority people, any ethnic minority groups, have poorer mental health outcomes compared to white majority population. And ethnic minority groups are also all report higher mental illness stigma due to religion, due to spiritual or traditional belief, and which lead to lower use of services. So we're curious about, for this seed grant, we are curious about how students from different racial and ethnic groups interact with this chatbot differently. And for minority students, because there is actually more stigma, would they be more comfortable if they're talking to a bot? So we want to ask the question of how does the expression of mental health concern differ based on whether they believe they are interacting with an AI versus a human? So, okay, almost there. So would there be a difference? And then second is, how does the expression vary across racial and ethnic groups? So, are minority students more likely to disclose more than to the computer, to the AI bot, than the therapist, or vice versa? So these are some of the research questions, and we'll do a 2x4 experiment based on self-report survey. We're also going to analyze the conversation script. So we're still trying to get IRB approval for this project. How fun. So yeah, so these are, the second is project is going to be a chatbot based on OpenAI's large language model. So, and we're exploring how to do it, and it's a seed grant, so not much money. So yeah, I think, doesn't matter old type of chatbot or the new large language model based chatbot. This technology offers an opportunity to provide personalized, tailored health education and promotion to people, ideally in a place that they're comfortable with, not in the doctor's office necessarily, but in their own house, on their own phone. So people are more likely to not feel judged or rushed, and then they can interact. They're available, and you can provide personalized like advices, support. Yeah. So I think this represents a good opportunity to combine the work on health promotion and artificial intelligence. So I am, still interested in these two general big question: how to design chatbot that is more effective in health promotion. So in things like, how do we make it more human-like, right? How to create more social presence for the chatbot, so that we have a more natural conversation, et cetera, and et cetera. The second general question that I'm interested in answering is how to understand the relationship between technical features and user characteristics. So what kind of technology works best for what kind of users to achieve a best end result. I think that is question. Yeah, question.
Thank you so much. I think there's a question.
So how are you collecting the training data? Because I assume you will need a large sample size for the training data to learn the chatbots efficiently.
For the new study, I don't have training data. It's just a pilot. We want to see if we can create a chatbot that more or less are a little bit similar to the therapist, because we want. So the hypothesis we're testing is how whether people will behave differently when we tell them that you are texting a chatbot versus you're texting a therapist in training, something like that. So down the road, we would like to have training data for the other project, the HPV vaccine study. A lot of the initial training data comes from the Texas Children's Hospital. Okay. The interaction, the transcript of the doctor, how doctors answer questions, the patient's parents ask, and then what kind of questions they ask, those data set. Yeah.
Question.
Hi, it's a very interesting talk, and I don't mean you should do all of this with your tiny, seed grants when you're just starting out, but I guess maybe this is for future work, something if you haven't thought about, I think is important for you to think about, or if you had, I'd like to get some insight. So when I work in health sector, which I do a lot, one of the difficulties is it's not the same as, let's say, my friends in grad school who went to work for, big companies to do marketing. They get whatever they get right, and whatever they get wrong is fine. If you go to Amazon and you're recommending books, you do the best you can. Hey, it's not a big deal if I got something wrong or not. But if you're in the health sector, whatever you're doing in this space, you have to have some minimum guarantees on safety. And so it's a very interesting talk. I can see this eventually somehow something happening, but I've had lots of interactions where hospitals would pilot a telemonitoring something or another, alerts go off. And after the pilot, they decide to not do this. And the reason is because if you have alerts coming into hospitals, and there was one alert that actually resulted in someone dying because the hospital didn't have enough staff to go through all the alerts. And so in the investigation, if they find actually you had an alert and you didn't get to the alert in the time that you needed to, which resulted in this thing, these are all serious consequences. So you just have to have some concept of there's a minimum thing you have to aim for, and you have to prove that you've met that minimum thing for it to actually make it out to the real world. And then in particular, you're working with mental health situations of counseling. These are very sensitive conversations that one misstep of the bot can send people off in really bad directions. And so I'm not saying you should solve this problem like from the get-go, but I'm just saying, if you have some thoughts on what kinds of minimum guarantees you want to be looking for and how you might go about doing that, I think it'll help direct your research in a more possible, feasible direction. Like if you think about it now versus like after you've figured everything out, it's hard to, do that. So this is what I struggle with the most when I work on stuff, because I'm not quite there yet, but again, I don't want to end up in a place where I can't get to where I need to be. So it's just something that you have to think about.
Well, thank you. So, yeah, to answer the question, yes, we did think about it. For the HPV study, all the scripts were reviewed by several, HPV specialists, pediatricians, and all that. So for the mental health, it's more tricky, but we're also just starting. So right now, the idea is, eventually, if we talk about the predictive ability of AI-based chatbot. So if there is a signal that there is like moderate level of mental stress, like, warrants the referral to a therapist, or because it's in college, so the university's counseling center, we will direct them to make an appointment at the counseling center. But this is just initial, some of the initial idea. I don't think this can deal with like serious mental illness. It's just general support for college students' mental health. Oh, there are too many exams, I don't have any money, or that kind of thing with like stress coping. Yeah, thank you.
Thank you. I'm sure there's going to be time afterwards for more discussion. So our next speaker is Professor James Kai from veterinary medicine and biomedical sciences. Thank you.
Thank you, Alyssa, for the introduction. Yes, I'm from YIBS and the ECEN, two departments. Today I'm going to take this time to give you some introduction about this single-cell technology change the life science overall, and to make life science more data-driving. And we can now to use data itself to establish the hypothesis to lead biological research. I mean, it's pretty different from the before. Okay, so it's the right time for the intersect of these two major technology revolutions. One is machine learning and another is single-cell technology. This technology has been around for almost several decades. And at the very beginning, we only be able to measure or assay the information from individual cells, but quite a small amount of cells. But nowadays, we can get the gene expression profile, for example, for thousands of genes in thousands of cells. This is because of this technology improvement by so-called droplet-based individual cell capture. And also, once you capture the cell, you lysis the cell and break it up and release mRNAs from it. And then you can have the small interaction, reaction among those individual cells. By using this barcoding system, you can tell each mRNA transcripts from which gene, from which cell at the end. So this changed the way people working on tissue samples, individual cells. Before, you have to smash all the tissue together to get a gene expression profile on average for individual genes. But now, because of this separation of the individual cells, you get thousands of cells and thousands of genes expression profile. So you get a matrix rather than a vector of the data. Data scientists really like matrix. We can play a lot of operations on the matrix. We cannot do much with vectors. This is like a view. I want you to have some idea of where the data come from, what the data structure looks like, what the data points looks like in general. So this is from one sample. You can think about any tissue from animal or human, and you spread this out to give you a whole matrix of the gene expression profile in many, many cells. This is just a very small corner of the size, this matrix, and the z-axis indicate how high this particular gene expressed. in particular cell. As I said, you have a lot of things can be done with data-driving approach with this matrix. But if you have two samples, for example, one from a healthy individual, another from diseased patient, and then you have two matrices put together, you get all the cells information for all the genes. And this makes the analysis more attractive. You can compare cross samples. Our ultimate goal is to quantify or define a score for individual cells to describe its states. So either this cell is more likely diseased states or more healthy states. And this will, because you have many, many cells, you create gradients and you can see, okay, there's a landscape of the cell states from healthy end to the diseased end, their intermediate stage. In this way, we ultimately want to see whether we have perturbation strategies can push some of those cell fate from disease states to more healthy states. So this is our global picture view about the single cell biology, and you try to understand individual cells states by looking at its gene expression profile and try to work out the dynamics of the cell gene expression, activity change profiling, and also see whether we have a perturbation and another strategy to push cell from one state to another. All right. So I was a geneticist and I changed my research and focus on the single cell biology using machine learning. I use a lot of MATLAB to do this modeling, build the interface for teaching, build this machine learning pipelines in order to do some of those analysis, make sense biologically. So this is like intersection of the research. So I will go through several examples to give you some concrete expression about what the data look like and how we deal with this. As I said, we developed these tools and for visualization purpose. So you can easily transform, process the matrix input into something like this 3D embedding. And that's help you to understand the relationship between cells if they are clustered together and they probably come from the same cell type or maybe from the same cell type, but also in the same states. So in this example, we have two samples from a different stage of development. And you can label the cell type. There are pipelines, machine learning tools. You can search for the marker gene database in order to assign different labels for cluster of cells to know, okay, which cell type they are. You can have this multi-dimensional view to look at the origin of the cell type and also origin of the cell batch ID and also the cell type side by side. This labeling will help biologists to understanding their data rather than just look at a spreadsheet like the table. This is very helpful, and biologists need to manipulate their data points themselves. They know what to do next after that. So there are some novel solutions that couldn't possible for traditional RNA sequencing analysis. For example, if you use bulk RNA-seq, we can do single sample experiments. Even you only have one sample from healthy individuals, for example, because you get a matrix. So that's information sometimes enough to tell you a lot of biology about the cell type and the cell states, activities, functions, something like this. If you have a matrix like this, you can compute genes mean and also their drop-off rates, variation, and you can look at the genes to fit with the curve. And then some genes will jump out of this curve. Most of genes will follow this pattern very nicely. So those genes jump out of this curve, we call outliers. Those genes are very informative in reality. Their expression profile not following every other gene's general rule. And those genes, for example, this particular example, these 3 genes, they are so-called Yamanaki factors we found from just N=1 experiment. And those are the important transcription factors and can lead to the Nobel Prize level of the discovery. So this transcription factor define the stem cells states. More complex machine learning tool, we can build those examples, and we made it into a series of tools so people can easily recognize them. This is called 24net. This is used to compare 2 gene regulatory networks. So we have 2 inputs. One is this matrix from single-cell RNA sequencing. One is color-coded in black, another in red. And we build so-called gene regulatory network using the method called principal component regression. So all the terms are machine learning related. And through this tensor decomposition and the reconstruct the matrix to denoise the data and use some nonlinear manifold alignment in order to align these 2 networks data. Yes. Then through that comparison of the position of the reduced dimension space of the gene location, we can prioritize those genes, which one responds for the change from one gene regulatory network to another. So if you compare 2 samples, you'll know what the differences are, rather than compare the average expression of a gene by itself. So in this case, we discovered the gene regulatory modules important for biology. And this is also another tool based on a similar idea, but this purpose is to do the so-called virtual knockout. In gene function research, people use knockout animals to delete one gene from this animal in order to understand the function of that gene. But we don't use animal, we just virtually delete a gene from the network. And so biologists can use this to predict the function of a gene before they really go to the animal experiments. This is evidence that we predict the function of that gene, which is exactly the same as you use animal to predict that genes. So there's a potential you can reduce the number of animal use in experiments. This tool is called XCT for interaction between different cell types. Again, this analysis wasn't possible if you use traditional RNA sequencing technology without the individual cells information, because we try to understand the different cell types interaction. So you need to have information from 2 different cell types there from the same tissue. Consider this as cancer cell against the immune cells, whether how they communicate to each other. This tool will help you to do that. Another direction we have already tried is to use quantum computing to build gene regulatory network. So this is a gate-based quantum computing framework. All right, with that information, I just illustrate a little small corner of this potential for biology, machine learning in the life science. Okay, thank you very much.
We're going to hold off on the questions. Our last but not least speaker is Professor Tapasree Roy Sarkar. She's also going to talk about single cell work. Thank you.
Howdy. Thank you so much for the invite. I'm really having a great time and learning so much. So today I'll be talking about advancing cancer research with single cell technology. My lab is working on tumor microenvironment. So I'm going to start with a very brief introduction. What is tumor microenvironment? What is the main focus of my lab?
So when we are talking about tumor microenvironment, it's not only tumor cells, but there are many other cells, for example, immune cells, cancer-associated fibroblast, extracellular matrix, blood vessels, they all are there in the tumor. And the interaction between them plays an extremely important role in tumor progression, metastasis, drug response. So our lab is mainly focusing on breast cancer, and based on the expression pattern of many marker, for example, estrogen receptor, progesterone receptor, or human epidermal growth factor receptor, the breast cancer can be broadly divided into 3 different types: luminal cancer, HER2 enriched, and the triple negative breast cancer. As you can see, this arrow indicated that when the tumors going from luminal to more basal direction, the aggressiveness increases, the mortality rate increases, the metastasis rate increases significantly. So mainly in my lab, we are working on triple negative breast cancer, which is the most aggressive types. We are also working on some aggressive HER2 breast cancer. So main focus is to try to see that on the role of tumor microenvironment in tumor progression and metastasis and drug response. We are mainly focusing on cancer-associated fibroblast types of cells. We also want to see that the impact of different environmental factors or drug treatment on tumor microenvironment, and also planning to use machine learning for accurately predicting drug response and patient outcome by using the patient data from MD Anderson. So first one is environmental factor. One most important one is circadian rhythm, which is the mental physiological changes the body, any organism that experiences within the 24-hour cycle. So this circadian rhythm is the one which controls our body function, our hormone secretion, metabolic activity, everything. The circadian rhythm it controls. So you can understand that any disruption in this rhythm can have serious consequences. It can cause different diseases, metabolic syndrome, cardiovascular disease, neurological disease, and cancer. And there are different ways this circadian rhythm can be disrupted. For example, if anyone is experiencing frequently jet lag by traveling across the zone a lot, or shift workers who are working at the night shift day after day for a longer period of time, those people, they can have this circadian rhythm is disrupted. So there are many epidemiological studies which shows that the flight attendants who are, they have reported, female flight attendant, they have reported elevated breast cancer risk. And then the shift worker, they have also high risk of cancer. Last year also, there is another paper came which showed the association between the circadian disruption and breast cancer. And in case of male, there is also incidence of prostate cancer. So my graduate student, Ola, and the postdoc, Mrinmoy, they were working on trying to see that one, what are the effect of circadian rhythm disruption on this aggressive triple negative breast cancer. And also, if we expose the normal mice to this circadian rhythm disruption condition, what is going to happen with their mammary gland? And what is the molecular mechanism? Because all those studies, whatever reported, those all are epidemiological studies, but there is no experimental studies which have showed that what is going on and what is the molecular mechanism behind that. So what we did, we used normal mice. We put them into the either the LD 12-12, that means 12-hour night, 12-hour day, normal condition that we all experience, or we put them into CRD, circadian rhythm disruption, where we followed a jet lag protocol, which is, which is a known protocol or established protocol. So where every 2 to 3 days, we give them 8 hours phase advanced, like the way the jet lag people, like the people who are experiencing jet lag, they mainly feel. So we observed that in case of normal mice, there are severe changes, severe disruption in the mammary gland when they experience the circadian rhythm disruption, which was a preliminary indication of their ductal hyperplasia or breast cancer. And in case of genetically engineered mouse model, we used a mouse model which has a record, or they normally spontaneously develop tumor at 24th week, the aggressive breast cell tumor. And we saw that when we put the mice either in LD condition or CRD condition, those mice which suffered the circadian rhythm disruption, there is an incidence of acceleration in the breast cancer. So they have a higher rate of breast cancer, early breast cancer, and their lungs are filled with, I'm sorry, this image didn't come here, but there was a lungs are full with metastatic nodules. So the metastasis rate also increased significantly. So we wanted to know what's going on in their microenvironment. So we did single-cell RNA-seq. James already explained what is single-cell RNA-seq. I'm not going into details. But what we did is we did the single-cell RNA-seq, and we saw that in compared to the LD tumor, the CRD tumor, there are certain types of cells, cancer cell, the cells which are known to induce the cancer progression or inhibit the immune property. Those cell properties, those cell population increase significantly. For example, cancer-associated fibroblast or M2 macrophages, those population increase significantly. We used another bioinformatic tools known as cell chat analysis, which showed the cell-cell interaction pattern. And that also showed that under the circadian rhythm disruption condition, some of the cells, their interaction with the other cells, that means the cells which are helping each other for the tumor progression, drug resistance, those cells interaction increased significantly in compared to the normal cells. We also used another tool known as GO or gene ontology, which also showed some of the signaling pathway, for example, heat shock signaling pathway or some metabolic signaling pathway. Those increase significantly under the circadian rhythm disruption condition. The tumor microenvironment become totally immunosuppressive. That means the immune cells, which are supposed to help to kill the tumor cells, their population decreased significantly, whereas the tumor cells, the cells which are helping in tumor progression, their population increased significantly. These are the CAF population, macrophage, or cytotoxic T cells, which is a good cells, which are helping always us to, by killing the foreign cells or even tumor cells, but those population decreased under the circadian rhythm disruption condition. The differential gene expression analysis showed the presence or expression of one gene that is called LILRB4, which is an immune receptor. That expression increased significantly. And we saw that its expression increase in the tumor samples or mammary gland, which are exposed to circadian disruption condition. And the downstream target of that gene also increased significantly. So we have the multiplexing immunostaining, which also showed that under the circadian rhythm disruption condition, tumors are very much immunosuppressive, and all this is helping in the further tumor progression and metastasis. Then we used a targeted immunotherapy against that LILRB4, that the immune receptor that increased significantly. So when we use this immunotherapy, we saw that the CRD-induced lung metastasis decreased significantly. So we here all together with the help of single-cell RNA-seq data, and we also followed by many other experiments just to confirm our data, we showed that under circadian rhythm disruption condition, the mammary gland become disrupted. It accelerated the tumor progression. By enhancing the LILRB4 signaling pathway. So after inhibiting this LILRB4, we were able to show that we can inhibit the circadian rhythm disruption induced tumor progression. So the next project, so that is, this one is just, we submitted yesterday actually bioRxiv, and we are in the process of submission in the journal. But this project is it's at its infancy stage, where we are trying to see the role of cancer-associated fibroblast in tumor progression, because we know that it is playing an important role in tumor progression, drug resistance. But there are multiple population of CAFs in the tumor microenvironment, and nobody knows which population is playing a role in the tumor progression. So what we did is our graduate student, Kayla and Harshini. So what they did, they isolated the mammary gland, and they harvested the mammary tumor at the different stages of development. And we did single-cell RNA-seq. And we saw that in compared to the normal plain mammary gland in the tumor, the cancer-associated fibroblast population increased. And when you are looking for which population, we saw S100A4, this expression containing fibroblast, cancer-associated fibroblast population increased significantly. So, and we try to see their expression pattern in human tumor sample also, and we saw that more aggressive the tumor, higher the population of S100A4. So it is somehow showing that it is having some role in the tumor progression. But right now, what we are doing is we, in collaboration with MD Anderson, Dr. Debu Tripathi and William Huang, who is an expert in the spatial field, and Bani, we are trying to, we're getting the human tumor samples from MD Anderson, and we're trying to find the CAP profile and the tumor microenvironment in those breast tumor using single nuclear RNA-seq and spatial using nanostring. So now I'm just going to give you very brief introduction. What is, yeah, what is spatial? So when we are doing RNA-seq, we are basically getting the expression pattern of transcriptomics as a whole. We know it's like a smoothie. So you know that you are having everything, but you don't know exactly what you are having. But single cell RNA-seq is giving you an idea of what are the different cells are there, like transcriptome patterns in each and every cells in that tumor microenvironment. So you know that what are the different fruits are there, but you don't know how they are organized. Whereas this spatial is going to give you an idea how the cells are organized in the field of inside the tumor. And why it is important. And Alicia was asking me why it is important. Why do you want to know? So there are some examples where two tumors, two breast tumor, similar types of tumor. One is sensitive towards any chemotherapeutic drugs. It's responding, but other one is not responding. So when the scientists, they try to see that one, what's going on, they observe that one tumor is immune inflamed. That means the tumor cells is a purple color here, and the green cells are immune cells, which are supposed to attack those tumor cells and kill those cells. They are in close proximity. So that makes them very sensitive towards any types of immunotherapeutic drugs. So drug can have a good effect, and they are sensitive towards, they're responding towards the that type of immunotherapeutic drugs. Whereas the immune cold condition, you can see that the cancer cells are completely in the not in the close proximity, or the immune cells are not infiltrating inside the tumor cells. So they are far from each other. That makes them cold. That means even you are using any immunotherapy, they are not going to have the similar effect. So they are resistant to a drug. So this information can only be possible with the spatial proteomics or transcriptomics, not via single cell RNA-seq. So that is what we are planning to do. And we are going to use nanostring, which is going to give this, this is the membrane staining. After the staining, they are going to do the cell segmentation. And finally, they are going to analyze the either via transcript or proteomics. They will give you the cell atlas, what are the different types of cells and how they are present in the tumor microenvironment. So we are going to use this SpaceGM, one of the machine learning tool, spatial cellular graph modeling, where they are going to use this GIN, graph isomorphism neural network, where they will, the orange color is the cells, one cell, and there you can see that there are 3 different stages of networking, where they're trying to see how the cells are interacting with each other on this tumor microenvironment. Finally, they merge them together to get the tumor microenvironment, and we will connect that information with some phenotype, for example, patient survival or the drug response. So together, our future direction is we are trying to identify the role of CAP population in tumor progression, the CAP in drug response, and identifying the tumor microenvironment in drug-treated tumor samples, and using the machine learning to identify specific pattern in drug resistance tumor sample. And this is my lab member. Here is my lab. Thank you so much.
That was great. Thank you. So now I think we do have time for questions and discussion, right? Go ahead.
So
Because I thought that was amazing, and the whole regulatory issue of how AI and it keeps changing, like a drug doesn't change. Even though this post-marketing,
How are you interacting with them, and what do you think are some regulatory mechanisms that can keep up with the fast pace of changing AI?
That's a very complicated question. So we can split up there are a lot of different approaches that you could use to regulate AI. And there are two broad camps and some mixtures of the two. But there's the traditional regulation, statute regulation, which is what we have done in traditional medical regulation with the FDA and licensure and credentialing and that sort of thing. That's a very slow mechanism. Alternatively, we see a lot of folks and scholars in AI governance looking more and more towards soft law, which are rules and standards that are often voluntary, and they lack the penalties and enforcement capabilities, which is one of the reasons why some are skeptical of them. But they can be adapted much more quickly because they aren't bound by the same sort of regulatory inertia that we might experience in typical government bodies. Now, I will say, I mentioned FDA earlier, they are exploring more and more with the sort of a soft law type of approach with some of the regulation of AI enabled medical devices, which is exciting from my perspective because there is a soft law component within a hard law regulatory structure. And I think it's going to be interesting to see how that develops and how some of the courts treat that. You see the UN is looking at global AI governance, and right now they've issued some preliminary reports, but there's still a lot of work to do. I think the EU's AI Act, which is a hard law framework, it's going to be interesting to see if that stands up as AI keeps developing.
Thank you. What? Okay, go ahead.
Yeah, so my question is to Cason because I think his talk touched it, but any of you can chip in. So when you are talking about ethics in AI, I was wondering about black box algorithms. So what do you think can be problems with applying, say, black box algorithm like deep learning to, say, health research? And do you think there is ever a possibility that actually those things will be used in hospitals?
Could you repeat that one more time?
Yeah, like black box algorithms, say, for example, deep learning or neural networks where you do not get a model, but they do the predictions, like they get the prediction done.
You guys aren't holding back
with the hard questions here. So one of the challenges when we think about, if we're approaching AI ethics from a purely utilitarian perspective, right? We got to have some understanding of what the risks and benefits are. And we can make guesses at this point of what the risks and benefits are going to be, but AI is really unpredictable, and the black box problem, as you've mentioned, is a really vexing component of that. And I think what's going to be essential moving forward is that, one, we're intentional with what we're doing. We're not just plugging in things that are developed in one context and plugging them in an entirely new context, because that could introduce an unpredictable risk. But we're very carefully monitoring the outcomes and being transparent when we do identify risks. So, for instance, one of the problems that we were trying to address in that science article was what tools can we use so that if we develop an AI system that is subsequently used by different actors or different applications, if one of them identifies a new and unexpected risk, how can we notify everybody who is using either that exact same system or a derivative of it that there is the likelihood of some risk? And we're just going to have to be very careful. And I think a lot of post-market surveillance is going to have to be essential in that regard. Because that's the only way we're going to uncover a lot of the risks that we don't yet know about.
Wow. I actually have a question myself. This is for Jason. So you were talking about all this wonderful data that one could collect, including health monitoring and to tell somebody, to see how people were doing this. What about privacy? I mean, I don't want you collecting my data.
That's a great question. That's why I deferred to my learned colleague, Cason Schmit. No, it really is a problem. Okay. And, we think about this, even with HIPAA and all of that. There's a caveat in HIPAA where you can use certain data regardless. If it's in I don't remember exactly the term, but essentially into public welfare. So, in the time of a disaster or things like that, I'm not saying HIPAA gets thrown out, but there's a loosening of how well that's monitored. But that's a real issue. And I was fortunate enough to work with Dr. Robin Murphy and Dr. Angela Clendenin and Dr. Paula DeWitt on a project where we were looking at the legalities and ethics of UAS and disaster situations coming off of our work on UAS and COVID, or of robotics and COVID. And this is an overarching issue. How do we use that data? And then, the other piece is if we're teaching machines how to learn, and we're doing machine learning, how do we get the data to feed into the machine and also protecting patient privacy? So it's a little bit different, but they're all kind of birds of a feather that we have to look at and be very careful. And part of it is on us as the research community to take extra care in protecting that data so that we don't violate the trust that's instilled within us.
Tough road to hoe, I think.
I do want to chime in a little bit here, the risk of taking too much time. I think we really need to rethink privacy in the age of AI. Traditionally, we've thought of privacy, and the way to protect privacy is to hide identifiers. In AI, in machine learning contexts, we don't need to know who you are to hurt you with the data that we have. And so I think to a certain extent, privacy is in danger of becoming a bit of a red herring, where it's a shiny object that distracts from some of the real risks and harms. And I think that, as Jason was alluding to there, in some ways, stewardship and governance is better protective mechanism than just hiding identifiers in the data that we have.
I don't know. Any comments on that? Because I am going to push back.
I have a kind of question on that is, the shift to large language models requires access to global data sets, but maybe something like federated learning, would be better for protecting information. What do you see the role? Well, what do you see the role of maybe smaller scale machine learning, smaller data set machine learning is in this field? Anyone?
So I think that it's a start, in places where we don't have anything. As long as we're looking at it and monitoring it, and keeping to adapt it, I think small scale, these small language, these small model AIs are useful, but they're a bridge to other tech, other AI that's a little bit more. There are dangers that are inherent with that. So depending on what you use for your data set. You know, you have biases that can't be wiped out as much as they can in a larger language model. But I think that in certain applications where we're trying to instill trust, where we're trying to instill usability, it's a start.
Question here. Oh, did somebody want to add anything to that? Okay, go ahead.
Hi, thank you. First of all, thank you all of you for the great presentation. I'm a researcher from School of Public Health. So my question is related to the public health, because I'm a community-based publicity researcher. So right now, my research focuses on how to use the AI or machine learning applied to the community. So the speaker will talk about how AI can help the researcher, to quickly identify the cell or how we can advance our research, and or how AI or machine learning can help us to do the data surveillance or help us to do the epidemiology study. But if we think about the community, it is not a question. I just want to share my experience and I want to get everyone, your opinion. Because recently my team got an NIH-funded grant. We just use AI and machine learning applied to the Asian community to help the Asian community to identify the mental health symptoms. Because mental health is a big stigma. People don't just disclose that they have mental illness issue. We want to use the clinical data to help the community, especially the local community physician, to identify these early symptoms. But the problems when we talk with the community, when we come to the community, first of all, the community don't have enough data for us to train our machine learning, to provide enough data, because a lot of situations, the patient don't provide the data. Not only the community, the clinic doesn't have data, just the patient, because they miss a lot of data when they come to the clinic. And this is the first barrier. We could not get enough or sufficient or good quality data. The second thing is the doctor, the health provider asks us the question, okay, Dr. Ma, even you team help us find the early symptom. You tell us, okay, if this patient has ABC conditions, this person already had a higher risk to develop a mental health, or maybe this person already have the mental health. But this is not, you just use big data to anticipate that. But it may be this person already recovered because they have enough social support. Or maybe this person, just maybe this is not applied to everyone. But in community, as a doctor, how I don't want to just talk to my patient and say, oh, because the AI or machine learning data tell me you are at high risk. So I need to send you to the psychologist. So this is just a thought, how AI or machine learning can really help them. And how, especially what is the intervention? If even the AI or machine learning tell them, okay, to help them to identify the high risk people, but what about the next step? Even you share your data, you share the result with the community partner, how we can really, what we can do for the next step, and how we really can help transform our research insight to the community. So this is
a good question.
Yeah, can I say something first? I want to talk to you after this. So actually, I was having the exact same conversation with a collaborator at Columbia who used to be here and left us to Columbia about, she's talking about how all this money is spent on AI research while no money is spent on community health promotion. We were working on an NIH grant on Latino mental health. So yeah, just something that I had the same conversation yesterday. I think with respect to these data set, I mean, I don't think this in what you describe, it's not. I don't think it's feasible for the doctor just to go to somebody, say you have a high risk for mental illness, remembering it's highly stigmatizing. the patients might be offended and they're like, change doctors. So I think, this communication, it's a communication problem, like how to get the message across without offending people, but like setting off the alarm. Like, I think part of it could be education, like just decrease the stigma in general, where then people, the minority populations are more likely to accept these like warnings and without being offended.
And just one more thing to add on, in my work with the federal and state public health departments and epidemiologists, some of this particular state at the state level, they don't necessarily need more data because they don't have the workforce to act on the data. And we saw that during COVID-19, where the public health system is just overwhelmed. And I think one of the dangers in the AI space is that we start learning so much, but we're not translating that knowledge into the socially beneficial, actions that really serve as the foundation for, in my context, public health surveillance. Public health surveillance without action that benefits the community isn't ethical surveillance. So anyway, but I think the goal is to find some way, and maybe this is the point of truly interdisciplinary research, is to work with the practitioners on the ground, work with the government public health authorities that are doing the type of outreach that might result in some real preventative health interventions. I think that's really important, and it's a dimension that we can't lose sight of as we start learning more and more from artificial intelligence.
And I think too, so the AI is simply, in my mind, another tool. It's just another tool, another diagnostic tool, another communicative tool, and something like that. So as we, I saw pictures recently of the first CT scan ever, and a CT scan that was done last week. And I mean, just think about the first CT scan was what, Dr. Sherman, 1971, something like that. And it was grainy, and you couldn't tell anything from it. And you saw this dark mass, kind of like the Loch Ness monster floating around. But my point is that over time we refined that, and over time we have used those tools with a human in the loop to say, this is a mass. This is something. And so as we continue to work with the tools that we have right now, we still have the human in the loop, and that does not abdicate, that does not allow our people, our healthcare providers, our clinicians, our community health workers to abdicate their ability to communicate to their patients. And that has to be, like I said, I don't trust AI to make that determination on whether or not I'm going to get radiation or not.
Question is for how would you think that nowadays, because of the fast advancement of generative AI, we are now very much concerned of deep fake information with the involvement of deep fake information and many setup agendas. So how you further trust the data in your hands?
Yeah.
So in single cell biology, you don't care of this generative AIs, right? And we try to regenerate these features for the cells as much as we can. So in that case, we try to understand what the individual cells is doing.
I had a related question, which is, how do you design a chatbot that is more convincing than all of that horrific misinformation that's out there?
right? That vaccines are going to kill you and who knows what else.
That's a very good question. I haven't done that myself, but a colleague of mine recently designed a chatbot to teach people about climate change. So she recruited people who don't believe in climate change and then let the bot talk to them. And then the bot was surprisingly convincing. Towards the end, it changed people's attitude. But those people were also very mad. They're very angry, but they accepted what the bot said. So, yeah.
Okay, yeah, that's interesting.
So we keep hearing it's not enough data, right? We have a rural community and it's not enough data or whatever. Some of the AI experts that I've talked about, we kind of spitballed this idea that, okay, let's take, 100 rural communities, get a base model, and then fine tune with smaller data. And I mean, you could see that in a lot of different aspects. What do our experts up here think about? How do we overcome small data in ways so that small rural communities and other small entities aren't left out?
It's called pre-training and reinforcement learning.
Well, I think that's kind of akin to well, you don't understand, my community's special problem. You don't understand, we have a very dry climate, or you don't understand, we get hurricanes all the time. And, it's about the data and being able to slice it and dice it and look at certain things. But again, I go back to, what's the purpose of integrating this technology in? Is it to get us close, where I'm sitting there and I for the first time in my life, I see a wide mediastinum in a dairy worker and I go, and they're having difficulty breathing, and this is 3 days in, and I go, never seen anything like that before. It's not cancer. I wonder what it could be. Oh my goodness. It's anthrax. Or am I trying to get the AI to tell me it's anthrax so that I, again, abdicate my responsibility as a clinician and a provider? So until we can get the algorithms to take and work with this small data set, I'm the guy who says you still have to have the human in the loop, and you cannot allow the humans to abdicate the responsibility.
So we heard a lot about the size of the data set, and this is going to show my statistical bent. What about the quality of the data that one uses to train algorithms? Because, you hear all kinds of horror stories, right? About, for example, algorithms to predict recidivism, for people in jail that use arrest data from past crimes and so on. Well, we all know who gets arrested and so on, right? So you keep perpetuating the same biases, except that amplified.
And so how do you deal with that?
I mean, where does that come in to the picture?
Well, one, I think it's prerequisite is you got to be honest that the biases exist in the first place. And I think for so many people, it's too convenient to pretend those biases don't exist. And the danger with AI is you're not just taking a bias and incorporating it into algorithm, but you're surrounding that algorithm by a black box, and you're using it to you're just structuralizing those existing inequities in an entirely new and non-transparent system. And I think there is a danger in, we've just got to keep monitoring the outcomes, and we got to keep measuring the impact of the algorithms. And we have to do so with intentionally and with skepticism of the results.
Thank you. Great discussion. Thank you, everybody.
Thank you.
So we are going to start our second spotlight session that focuses on AI and machine learning. And our chair is going to be Tracy Hammer, and she is a professor in computer science. And her work also focuses on AI.
Thank you. Thank you very much. And I will tell you that I recently lost my voice because I was sick over spring break, but I'm not sick anymore. I always lose my voice after I get sick for a long time. And I always get sick every time there's a vacation because I always like to burn the candle on too many ends with work and stuff like that. But anyway, I'm super excited to be here with you today. I'm also super excited for our first speaker, Marcia Ori, who is a longtime friend and collaborator who does many impressive things in health and is a distinguished, actually a Regents and distinguished professor. Sorry, and so I'm very excited to hear her talk. We're limiting it only again to technical questions right after this, and then we'll do a full panel of more interesting questions after the individual talks. So without further ado, maybe there's a little bit further ado.
Sing, so you'll have to dance, Tracy. Well, there you go.
There you go. All right, well, I'll give you a cheat of one of the questions that I was thinking about asking. So, and then maybe that way they can think about it. AI, the definition of AI and machine learning tends to be a very personal one. And the way I define it as AI is sort of this evolving field that things jump in and out of AI. I define AI as something that's really hard for a computer, but for whatever reason, completely natural and super easy for a human to do. And so that because that's how I define it, it means that something can start in AI and then fall out. And I also think of machine learning as fancy statistics. So for those speakers, maybe think about how you might define AI personally or on yourself, because everybody has their own sort of way that they define what AI is. And I think that that's a nice little personal question for later. Okay, but now Ori is ready, so.
Okay, thank you so much. I am absolutely delighted to be here. Can people in the back hear me? I got to hear the tail end of the last session, and it looks like it's been a great day already. So what am I going to do? You know, I think there was an earlier panel that said, what is collaboration? For me, the ideal collaboration is really when you can match expertise. If you think about the concepts, the methods, the approaches, and because I'm in public health, it is to solve a major public health issue. And so think about the kinds of people who bring different concepts, methods together to add synergy. And I think it's important to say what I am and what I'm not. I'm a social gerontologist. I do public health and aging. I'm really interested in implementation research, which is getting research into practice. But what I'm not is a data scientist. But what I see in the room are there probably lots of other data scientists. And I think the whole reason for this conference, this summit, is to bring people with content and programs and sort of data science skills together. So let me tell you a little bit about the center I'm in. It's a center for community health and aging. And we have a whole mission about improving the health and aging across the life course. But we do that by looking at capacity, whether it's in building capacity, whether we're talking about individuals, organizations, or communities itself. And what I would say is the important thing is to identify whether it's social, behavioral, environmental, technology, sort of determinants of health, and then think of their solutions. And this just gives you a sense of who some of the core aging faculty are. And my colleague, Jung-Hong Kim, is really more into kinds of AI and machine learning. He regrets not being here, but he welcomes follow-up collaborations. So what kinds of research topics do we deal with? You name a topic that's associated with healthy aging, and I probably have done it or could potentially be interested in doing it. So whether it's Alzheimer's disease, related dementias, environment, health, and aging, and I'm delighted to see my colleague, Dr. Wei Li, is going to be talking about environment and urban planning. So I'm not going to be talking about that. The other thing would be, everybody was interested in COVID-19. What I'm really interested in is evidence-based research, prevention research. So think of all of those lifestyle behaviors that we know are associated with chronic illnesses, disability, mortality. Health equity, I think we're all interested in that. Health technology, and the examples I'm going to be giving are more health technology oriented, but also around injury prevention and control. I'll be giving an example of fall prevention, opioid use disorders, and then women's health and aging. So these are the kinds of research I've done and many of my colleagues have done. So I'm in public health. We all know that there are lots of public health problems there. We don't end with the problem. We see a problem as an opportunity for action and solution. So what I'd like to do is just walk through some examples of research. It'll give you a sense of the kinds of research I do. Many of these research topics had colleagues that were into data science and AI. But it'll give you a sense of what can you do to really promote independence across the life course and also reduce caregiver burdens. So I'll be talking about a fall detection and prevention study, a Alzheimer's caregiver study, a sort of online behavioral skills training program, and then a really creative jigsaw puzzle. So the whole concept here is, and most of these, what's interesting is if you want to know about funding, in my field, if you have a very practical project and a colleague who's in business, the easiest and fastest way to get funded is through the SBIR mechanism. So the ones I'll be talking about have been primarily funded through SBIR. Do people know what SBIR is? Small Business Innovative Research Projects. And so the first one is really focused on the public health problem of falls. And the concept is, how can you use a creative, novel, new technology to both detect falls and then predict their occurrence in the future? And so there are two phases in many of these SBIRs. The first is to test out the acceptability, the usability of your tool, and then to look at its efficacy. So what these colleagues are doing, and it's actually clairvoyant networks, they're using ultraband radar. So they say this is more accurate. So I think many of us might have smart watches. They're saying this is much more accurate. I think of a smoke alarm, something that you would put up in the ceiling that could attach to a fob. The fob is worn on the body, and it will be trained to find out when people are falling. So you have the ultraband, imagine in like a smoke detector kind of on the wall. What they've done is they've worked with engineers and computer scientists, do a whole neural network of which I understand very little, but I know that they want to use that to understand body movements. And once they understand the body movements, they can alert people about whether you're on the floor, how long you've been on the floor, what were you doing before you fell. All of these things are more precise than, say, just the alarm that only tells you you're on the floor. This will tell you the pattern of movement along a trajectory. So they've got three different things they're doing. First of all, they're using one of these dummies where they just keep dropping the dummy from different positions, having it fall different ways, and to see if they can, if their tool can actually detect the fall in a laboratory setting where nobody gets hurt. just that poor Randy Andy dummy who's being dropped something like 150 times, right? Then they're going to move, and I love this, in April to work with people on the judo team. And I think we all have to think about the ethics of doing research. We want to see if the device will detect falls, but we have to have people falling safely. So we went to the judo team. They know how to fall, and we're actually going to be having them do a whole circuit of movement, which will include forward falls and backward falls, one side to the other, and we'll see if through the neural network, the device can pick up falling. And then the third, which is going to probably be the hardest to get through IRB, is when we actually get older adults in the study, and we're not going to have them fall, but they're going to do a circuit and a variety of movements where the fob will be able to detect the different movements, and then they will see through observation and what the sensor does, what's actually happening. So right now we're still in phase 1, which is the experiment of does it work? And then afterwards, we're going to go into the community and work with people, as you would say, in the wild, like 60 older adults who are not part of a study, but are living every day in their own homes. So AleraCare is another one of my favorite projects, and it is dealing with this problem. If you're helping somebody with Alzheimer's, there is so much information out there. It's overwhelming. Already as the caregiver, you are overwhelmed with trying to provide care. But how is it that you seek care that is more tailored and targeted to what your need is? So what they've done is to use a sort of personalized educational system, which they are, and the people who have done this, it's an interesting collaboration between people in engineering and people in clinical medicine. And they've come together knowing about the condition as well as knowing about the tool. And here they sort of scoop up all kinds of data about what do you say you can do for caregiving. And then you ask a question and it feeds you back very tailored information. So the first thing they did, and I think this is very common in my field, is to do an assessment of what people need. So the first thing they did was to get people online to say, you're a caregiver, what are your needs? So how can they know what information to pull unless they know what people want to hear? And then, of course, they always ask for usability studies. How do people like the tool? I think I heard Jason saying AI is just a tool. Well, I think this is just a tool. There are all these tools out there, but you have to make sure that the tool is acceptable to the population and they can use it and they like to use it and they would use it. So the future, they have had 2 phases of the SBIR, and they got funded for a 3rd phase, which is more the commercialization phase. And here I don't really understand the details, but they're going to use AI agents to basically help in elder care planning. So they are training what they have learned in phase 1 and 2 to better specify what care plans should be. And I think that's typical of what a lot of people do in health. They drag in all kinds of information so they can provide better feedback. And this is an example. The game plan for care. This is a colleague, again, who's working with dementia care. He had actually done this when I spent 20 years at NIH. And when I was at NIH, they developed a project that was called REACH, which was a caregiver sort of skills building program. Well, that only reaches so many people. So their concept is, how can we build an online system that will have much further reach, but actually have the same, if not better, efficacy? So this is at Baylor Scott and White. And what they've done is they spent a whole year working with their digital health team. the first thing they did is to understand the therapeutic content. What is it that caregivers needed to know? But just like with the AleraCare, it's the same concept. There is way too much information out there. So you ask a particular question about driving, it knows at what stage the person is, and it gives you feedback according to an algorithm of what you've already said. Okay, and this one, again, it's a tool that people like. There's been a lot of usage of it. What they want to do in the future is to sort of ask this question about when is it that caregivers are going to seek digital technology, and does it matter, when is it most valuable? So again, I think that we need to understand that we have tools out there, but when do people use them? Why do they use them? And what is most useful? And in what setting? This was in a community setting, but they also want to see if a tool like this would work when you're being discharged from a hospital setting. Jigsaw, this is another great study. It's one, so imagine, how many times have you heard in the news about brain health? What are the kind of best things you can do for brain health? People talk about being engaged in puzzles. Well, puzzles are often static, but think of this as electronic puzzles where your family comes together and it develops memories for you. So you say, Mom, what's your favorite spot or your favorite flower? So you talk to, the caregiver works with the person living with dementia. They come together, they build a sort of picture of the person's memorable events. But what's even better about it is you put the puzzle together and it talks to you. Hey, remember that trip we took to the beach? Or your grandson loves you, or your flowers are beautiful. So again, it's a way of automating memories for people with cognitive impairment. And again, the kind of outcomes which I think are important to understand. Why do we do this? We want to make a difference in people's lives. So this thing already shows improvement both in cognition and in depression. But the question to ask yourselves, and what I would like to know, is right now it takes forever to put these puzzles together, and caregivers are too burdened sometimes to do it. Well, could you use AI, machine learning, any technology to sort of speed up the process of putting memories together that are still memorable? And then what is the future? There are so many different projects. As I say, almost every public health problem I could be interested in or have been interested in. But right now I'm working on a project in Nigeria where they're trying to understand how to disseminate vaccine preventable, how to prevent vaccine preventable diseases. And they're doing this by trying to figure out where and what time they should distribute vaccines through a whole country. Who's at highest risk, where there's likely to be an outbreak. And so for this and the next project, they're trying to build a portal, and we're actually working with people in T's to try to get a portal that will have information about where the disease is, what is the prevalence of the disease, where the vaccines are, how they're distributed, how, there might be an outbreak in the community next to you, how to get the information back and forth. So it's my colleague, Joy Alonso, who's working on this portal. We want to do something similar for opioid overdoses. We know that naloxone can save a life, but the issue is knowing where you should distribute naloxone in a community. Once it's distributed, what difference does it make? It's that tracking and monitoring, and then also trying to predict where the next outbreak might be. So that gives you a sense of the public health and aging projects that I work with. I assume we will wait to talk about collaborations. Thank you so much.
Thank you so much. That was a wonderful talk. We are running a little bit tight on time. So unless there's a hugely burning question, I would hope that you could wait until the panel time. But we now welcome our next speaker, Wei Li, who is in landscape architecture and urban planning, to give his talk.
Did you want?
Hello, hello. Good afternoon, everybody. My name is Wei Li. I am Associate Professor of Transportation Planning. I have been teaching transportation planning at A&M for 12 years now. My first name is Wei, so my colleagues always want to remind me that I don't forget what I do, so they call me, "Hi Wei, how are you doing?" when they see me. I was born and raised in a small town, and so I always have deep compassion to help the people who live in these underserved communities. So because I'm a nerd and I teach urban planning, so I want to ask you guys a question. How many small towns are there in the United States? If we define small town as a city with less than 50,000 people, 50,000 people, how many small towns are there in the United States? I give one volunteer. 5,000? 5,000 small towns. Okay. Another volunteer. 10,000. All right. So let's take a look. In the US, there are about 19,000 small towns with a population of less than 50,000 people. And they're homes to about 80 million people. That's a huge market for technologies, for innovation. But think about, if we talk about a smart city, I say, hey, let's build a smart city. You will think about a city like Boston, San Francisco. You won't think about a small town with 2 stop signs and 4 churches, right? And people will not associate with innovation with the small towns. And I think that's something that I want to change, because I think the technologies probably will better serve people in those small towns. So one of the things that I feel very passionate about is how to use automation to solve transportation problems, or how do we use autonomous vehicles to serve people. But if we think about autonomous vehicles, which are currently serving people, they are targeting the largest cities where public transportation is already very good, where people have so many choices, where so many Uber and Lyft drivers are serving people. And these autonomous driving companies will go there and say, hey, we're going to steal your jobs. Be careful. And that's why the autonomous driving industry is not doing very well. But they are not talking about the small towns, because they think a small town don't have enough market. Same to telemedicine. We think, hey, telemedicine is such a great thing. You don't have to go to see a doctor. You can see a doctor on your phone. But think about the small towns, rural areas, people who don't have this access to technology. They won't be able to figure out how to use telemedicine. So I think this is something fundamental I want to change. So 7 years ago, when I started to have this idea to implement autonomous driving in small towns, I approached a lot of companies, autonomous driving companies. Some of them even came to A&M campus for a demonstration. So I asked them, do you think we can have any demonstration in a small town? I have a small town. I can introduce you guys there. How about we do some demonstration? They say, no. I said, how about for one weekend, just 2 days? I'll provide a tow truck and everything will be taken care of. And they say, you cannot afford it. And I was like, hey, I'm an Aggie. I don't take no for an answer. And at that time, I read a book to my kids. And the book is called A Little Red Hen. How many of you have read A Little Red Hen? Raise your hands, your parents. I like the phrase, when I read that, a little red hen got refused by everybody, because he wants to grow the wheat and he wants to make the bread. And he said, oh, well, I'll do it all by myself. So after being refused by so many people at that time, so many years ago, I was determined to create a demonstration project that applies autonomous driving technology to a small town. And in 2020, during the pandemic, we launched a program called Endeavor Ride in a small town with 5,000 people in Central Texas. It's called Nolanville, between Killeen and Temple. So this is the vehicle, and it is for Transit Connect. So we put autonomous driving technology on it. We also equip the vehicle with the telemedicine technologies, so people can actually see a doctor inside the van, or can receive a telemedicine technology delivered by the van. And so people love it. People love the small town people, kids, people, residents, leaders, they all love it because this is something they feel like, hey, this is so much fun. And it is because the program is owned by the community. It is funded by a small town, which doesn't have a very big budget. And so we keep that in mind. We keep the whole program run by the city, operated and maintained by the city with support from Endeavor. And so this is the tailgate clinic area where people can see a doctor in the tailgate area. And so we have a partition behind the first row of seat where we hook up in the devices to take the vital signs. And people can see a doctor sitting on the second row or in the tailgate area, or we can deliver a tablet to people's home. They can see a doctor at home. And they can reserve a service through the app, text, or a phone call, where text message is the most often used among the three approaches. So this is a vehicle that provides telehealth care to people who don't have access to it. But at the same time, it is a vehicle that delivers a on-demand transportation services. It can bring people to the essential destinations in the town or near the town. That most of the users of this program are the older adults who are over 60 years old and or have some level of a disability, and they are not able to drive or enjoy this, the private vehicle. So on a monthly basis, we deliver about 100 trips. So most of the trips are located. This is the map of all the trips located from this different people's home to different areas. Most of the trips are to go to grocery shopping or to see a doctor. So those are the key destinations: HEB, Baylor Scott and White, Seton Medical Center, Walmart, Sam's Club, all these places. And so during the pandemic, the hospital is run out of capacity, and the city is very concerned about not having enough services to people. They say, hey, you have the telehealth van. That's wonderful technology. Do you think we can set up something inside a city hall where people can also see a doctor there? I say, yeah, let's do it. So with less than $10,000, we set up telemedicine booth there using a sound blanket and PVC pipes. It's cheap, but it works. You don't need a very fancy stuff to make things work. So that's what it looked like in the telehealth booth inside the city hall. And so this program is maintained largely by volunteers from the community. So Irene is one of our volunteers. So he provided a lot of rides to people during the pandemic to vaccination or to COVID testing. So he's awesome. This is the scene. I don't think we can play the video, but yeah, but I love Irene. Everybody loves Irene. He's great. And now later on, he has an eye problem. He was not able to drive anymore. And she became our user of this program. She just had a successful surgery. Now her eyes have been restored back to normal. Now she's a driver again. So I love these kind of things because you have to create something. If you want to sustain it long-term in the community, it has to be owned by the community. It has to be maintained by the community. It has to become something that people love it and people want to get involved with it. So in terms of the autonomous driving technologies, so currently it has the level 2 autonomous driving technologies provided as a in-kind donation from the industry, and the technology that are developed through this program are open source, which means that it can be replicated to serve other communities with a very affordable cost. So we don't talk expensive thoughts, we don't talk expensive ideas. We want to create some ideas where a small town with 5,000 people can own it. That's the philosophy. So why do you bother developing autonomous driving? Waymo is doing it, Cruise is doing it. They're so awesome. They are in Austin. You take a ride, it's so awesome. Yes, they are awesome. They will probably provide autonomous driving services to a lot of people. I'm very, very happy for them. And they are just like H-E-B or Kroger or Walmart, where most people go shopping for groceries. But imagine every small town, every city, big or small, there is always a food bank, right? Always a food bank. Why does a food bank exist? Because people need it, because the market is not able to provide to them. And that is my aspiration, that's to use this program, make this program as a food bank version of autonomous driving, serving communities. And we engage communities, college communities. We engage a lot of computer science students, including 2 teams from Dr. Hammond's class, to develop the autonomous driving technology and make it open source. And we also engage the community. We engage the retired teachers, the high school students to develop autonomous driving. And so there is students who are now exploring ways to develop technology by engaging the community members. So they can help us to train the AI models, the perception models, computer vision models for autonomous driving. So we got a donation of this big bus. So the next 5 years, we want to develop a fixed route autonomous driving services, serving Nolanville and the surrounding areas. And we have been very closely engaging communities and brought several honors to A&M and a lot of demonstrations in the community. This is in an event where Congressman Carter was there and the Central Texas area. A lot of demos programs where students from A&M are able to engage closely with the community members. So we also understand how we're doing by engaging community members. You recognize Dr. Marcia is there, and she is the facilitator of this folks group in Nolanville. By far, we have trained over 300 A&M students from more than 10 different majors through the programs like this. And it is my passion because I love doing chores to people. I love doing chores to people who have the technology, who also have the passion to bring their technology to small rural towns. So, and if you are interested in implementing your smart city technology, your AI machine learning technologies and turn it into solutions, I would love to do chores and introduce you to one of those 18,000 small towns, because that's something that I feel very deeply passionate about. It is a community-run program. So this is our YouTube channel and LinkedIn. And the picture is the kids who are doing fundraising for Endeavor by selling goodies in a garage sale in Pebble Creek. So with that, I'll conclude my presentation. Thank you very much.
Thank you so much, Wei. That was a wonderful, wonderful. Thank you for mentioning about the class. I was about to mention it at the closing about how we are also collaborating together, just like Marcia Ori has been a collaborator of mine in the past. But yeah, wonderful talk. We're again sort of squeezed for time unless there's a burning question. I would prefer to wait for the panel so that there can be some interesting questions to put together. Thank you so much again. And next, we just had 2 collaborators. Now we have a colleague of mine, Sing-Hoi, who will be talking about his research. He is an expert in AI and doing some really fascinating stuff. So take it away.
Hello. Let's go back to biology a little bit. Like when people talk about AI these days, I think you surely think about big data, a lot of data, large scale, and things like that. And what I want to show in this presentation is that those small data are still very useful, and biologists are still very much interested in them as well. When you think about human health, a lot of people think about like what happens through life, what are aging, what do we have in aging, okay? It turns out that we can also learn a lot to see what happens after death. So this is what I'm going to do today. The word postmortem means after death. The microbiome, there's another keyword, there's a microbiome. It's a bacterial community that's around a certain environment. It's very important because even before we are born, in the embryo stage, we're surrounded by a microbiome, which is a collection of bacteria that will be beneficial to us. And that changes over time when during aging and development, and also it also has some changes even after death. Okay, and why we're interested in this? Because a lot of time in forensic science, after you discover that body, what you want to know, the most important thing that usually you want to know is like, when did that death happen? Okay, and that's called a postmortem interval. Okay, that's what a lot of the people in forensic science are interested in. And this is in collaboration with Aaron Teron in entomology. And you may be asking why this is related to entomology. Entomology is a study of insects, isn't it? So those are a lot of flies, and you can imagine that flies appears all along the way during decomposition. So then it relates to the bacteria because they have interaction between the bacteria and all those flies. So that's why all these are relevant to them. Okay. What I must be saying is that what I'm going to present today is relatively simple in terms of the computational method that we're going to use, but the biological question we're trying to answer is by no means easy. Okay. Most of this work are being done by the first author there, who is one of my master student. She has a background, she's kind of a special. She has a background in public health because she became a computer science student. And this kind of project, which we just use mostly just existing methods, is suitable for example, master thesis, or our department, our computer science department has a lot of honor students, and a lot of them are also interested in this kind of approaches that apply methods to study biology without really discovering new approaches. Discovering new approaches is very difficult, and most of the time you will need the whole PhD to be able to do that. Okay. The data comes from 118 individuals, actually 188 individuals. So you can think of this as actually a small data. It's not really big data at all. Okay. And for these cases, they spread along different categories. For example, they have different age, different manner of death, and all these different kind of categories. And PMI there means a postmortem interval, which is defined as the time since death. Okay, so the unit there between the few categories, those are hours. Okay, and there are few period of times that people are interested in. For each of these 188 individuals, so you have all this data throughout these different categories. Okay, so what we want to do is that we think of those data that we've seen before as metadata. Okay, so for each of the individual, then we're trying to extract DNA from them. Okay, all of these you can think of them, those are bodies, isn't it? So we're going to do swabs in different areas in the body to get DNA from them. Okay. There's a special kind of DNA sequences which come from so-called 16S RNA. Okay, those are specific to bacteria, and there's also a few in the area which is called taxonomy classification, which you given some number of these 16S sequences is trying to predict what are the bacterial compositions within those DNA sequences. Okay. And this is in itself quite a challenging computational problem because those 16S sequences could be very similar even within related species, very related species under the same genus. Okay, but there are already some existing software that can be used to do that. Okay, so what we do here is that we just take those sample which comes in the form of file of consisting of DNA sequences, then we run those software to predict to do taxonomy classification and find what the bacterial compositions are in there. So what the biologists are interested in is, are there any of these bacteria that can be served as the indicator of these different categories? For example, this PMI, this postmortem interval, you have different intervals. Are there any specific bacteria that would be helpful for us to identify what's the time of death, for example? Okay, and you can see that in the picture there on the right-hand side, on the top of them, there's a one which has a red on one of these places, and all these others are almost zero. That bacteria is a very good indicator of that particular time period of death. Okay, and you can see some other examples there as well. We could also do this with respect to other things other than PMI. We can, I think it works only on this side. And we can also apply this to manner of death, and we can also do a similar thing. It's fine. So there are different ways that you can do that. The method that we try to identify this bacteria is that we have the metadata and we also have the bacterial composition. What we do is that we can build a model out of it. For example, you can do a very simple regression model, or you can use some of those machine learning models. And by these machine learning models, because the data is small, we use the traditional machine learning models. The one that we include, one is called XGBoost, which is a very good software that has demonstrated very good performance in many areas. There's another one called Random Forest, which we have seen that in our experiments, we've seen that the performance is not as good, but it's pretty much standard in the area. So everyone uses the Random Forest. So in some sense, biologists don't always use the software that we develop that are the best. They use the one that they are most familiar with. I think one very good example is the software BLAST. I think a lot of you know. So BLAST is used to, given a query sequence, try to find other sequence in the database that's similar to it. Okay, and over the years, there are many new software that have been developed. There are some of them shown to have better performance than BLAST, but people are still using the same thing basically all the time. So one of the important question we want to answer is there a software that maybe a model that consistently will perform better over others, or is the one that people use, the standard one that people use as good enough or not? So in order to compare it to maybe some of the more latest machine learning model, we also test it on neural network as well. But neural network suffers from a problem that for small data, it's hard to get a very good performance because you typically need a lot of parameters. A neural network has a lot of parameters, especially those deep neural networks where you have a lot of layers. Okay, so the neural network that we're using here is pretty simple, where you only have very small. So those are small neural networks. So we are not doing anything big here. So this is kind of a result that we're trying to see. Okay, there are 5 different areas that we got the swab from. It includes eyes, mouth, nose, and some of the other places. And we're going to use 3 machine learning models, which I just already say. And biologists want to see, for example, whenever you use one of these machine learning models, whether it works well or not. And this is so-called confusion matrix. I think a lot of you are familiar with. And these 3 numbers in slashes, they are the performance from these different machine learning models. And we're trying to predict PMI, which is the first one, event, location, and manner of death. And the diagonal values show the one that are predicted correctly, whereas the ones not at the diagonal shows the one that are incorrect. Okay, and I think from this table, it's not very clear which method is the best. In fact, there's another way to try to evaluate it, is to try to think of it in terms of the accuracy. You can define accuracy of any of these machine learning model. And we actually found that the random forest model that people use as standard is just in the middle in terms of the performance. And it's a little bit surprising that neural network actually does not perform as well as random forest. I guess for people who work in AI, a lot of people always think that you should use this large machine learning model as complicated as possible to get the best performance. But in reality, it's not always the case. So when you only have small model, it's very dangerous to use machine learning models that has that you need to fit a lot of parameters. You will tend to do overfitting and things like that. In the end, we found that XGBoost actually has a better performance than the one that's a standard one. Okay. And in fact, if you look at the common feature, these are the top 100 features that come from each of the different machine learning model. If you look at them, you will see that there are some overlaps, but also each of the machine learning model have different features that are important, which is kind of distinct from one another. Okay, I think one of the very good reason why we're using this traditional model is that it's often easier to try to predict to find the important features. Some of the newer machine learning model, which are those large language model, a lot of people think of them as black box. Of course, when research progresses, I think people have found ways to try to do something similar to finding the features yet, but it's considerably more difficult for those new models, which especially for the neural network, which we don't understand, because in a neural network we try to find those weights, isn't it? And weights are just a bunch of numbers. How to do an interpretation from there? So this kind of simple model still will be useful. In addition to doing this kind of investigations, because we are making swaps in different locations, and there are 5 different locations of swaps. And after we do a swap in each of these locations, we need to sequence. We need to get the DNA sequence. So the biologists are also interested to see whether we should get the swap from multiple locations, how many locations are needed to get an accurate result, and things like that. So in order to find to investigate this, we use an iterative approach. So first, we try to find the best area. We have 5 areas. We first find the best area that's most informative. Then afterwards, we add an additional area to the first area and try to find the best area again. Okay, we iterative this through all these 5 areas. It turns out that sometimes the performance could be unstable. You can see that on the left-hand side, the XGBoost model, in fact, the performance is decrease, and when you have more than 3 of those sub-areas that you're using, the performance increase a lot. So it's kind of not very clear what method we should use in a lot of cases, although the accuracy seems to be in general, if we're using all the 5 areas, XGBoost is always the best. But if you use less, it's hard to say. I think we also see in some other areas that I guess people use different machine learning models, and there's no conclusive conclusion of which method is always the best. I guess this is kind of a little bit hard to see. I think over time, I mean, I'm done. Okay.
Thank you very much for that very interesting talk. It's a very unique use of AI that I hadn't seen before, so quite interesting. We are again at sort of the exact time, so if there are burning questions, you can do one, but it'd be better if we could potentially wait until the end to ask a number of questions. Okay, Xiaoning, our next speaker. I'm looking forward to hearing your talk.
Thanks so much.
Sorry,
No, it's good. I have the same problem. Right. So thank you very much. Good afternoon, and let me thank organizers again to organize this wonderful workshop to promote collaboration. I do hope that I can get more future interactions with all of you. Actually, for my presentation, actually, I did not know originally what's the main topic I should talk about. So I focused on the omics data analysis in the sense that we're looking at the molecular level instead of a population level, individual level health care issues. So, but before I talk about the omics data analysis, this is typically like my kind of dream of doing AI machine learning model. Essentially, what I want to do is trying to basically integrate not only data, but also prior knowledge, expertise, and as well as the literature, right? So like everyone talks about the ChatGPT, so it could be a great tool to summarize whatever literature so that you get the relevant prior knowledge so that it can help you to do a better system modeling. So specifically, what we are trying to do is first try to build a digital twin or surrogate model so that we can understand the behavior characteristics of a specific complex system. And then based on that understanding, we want to do some intervention decision making so that we can make things better in a sense. Right. So of course, there are lots of different issues. For example, in complex systems, typically you don't have large data. It's not like the internet literature. There's enough data so that you can train your ChatGPT. But if you are looking at a specific disease, especially for those rare diseases, you don't really have that many data points. So for those kind of problems, indeed, integrating prior knowledge, expert experience is important to have a faithful, high fidelity surrogate models. And of course, there are different machine learning AI solution strategies when you are trying to address this small data issue. For example, transfer learning, context learning. Recently, people are trying to come up with different solution strategies. But overall, I guess I consider like doing scientific research is this kind of iterative procedure, right? You do some modeling, you check your model to see how it performs, but at the end, you may lack some knowledge, you may lack some data. You need to find smarter ways to acquire the data, acquire the knowledge so that you can do better decision in future. And to be specific on healthcare, so essentially, this is one of our DARPA projects trying to do the context-aware health monitoring. So essentially, what we are trying to do is to integrate whatever possible sensing data as well as health-related data into our model. And firstly, you need to do lots of data pre-processing based on the data types. And then at the end, you need to build up an AI machine learning model to basically estimate the risk or whatever health status you are trying to monitor. So they are definitely involving probabilistic models, not only AI machine learning model in the sense. Traditional statistical models are very important to look at different data types and try to integrate them together. And specifically, if we are looking at the omics data, it could be genomic data, it could be proteomic data, it could be metabolomic data. So based on different data types, essentially, at least in my group, we are trying to specifically model those different data types, not just using Gaussian distribution to model all the data types. In fact, I want to basically explicitly have a different probabilistic models for different data types. And then at the end, when you model those different data types, hopefully there is a way to do the integrative analysis by data fusion. Right, so typically what people do is to put it in a latent space. And then from that latent space, you can derive whatever risk model so that you integrate all the data types to give you a more reproducible, more reliable, accurate risk score at the end. So I'm showing here just like really one old example when we are looking at the SNP data. SNP data is categorical, right? So I'm just simply comparing categorical PCA we developed with Gaussian-based PCA, just to consider 0, 1, 2 as a continuous Gaussian random variables. So you can see that, in fact, if you explicitly model the categorical nature of the SNP data, you indeed can do better risk score estimation, essentially. So yes, this is kind of the what I'm thinking about doing AI machine learning models or the general probabilistic models for specific data types. And for today's talk, I will start with the next generation sequencing review. And because the main part of this talk is about how to use new generative models to analyze omics data. And the omics data we are trying to analyze is basically RNA sequencing data or like single cell RNA sequencing data. And then I'll talk a little bit about what models we have developed in the past 5-6 years. for those different data types. And then I'll focus on how I integrate the prior knowledge, biological knowledge into the machine learning models so that we can generate better results, right? So yeah, so I'm mostly just focusing on RNA sequencing technologies that happened in the past few years. So essentially, the next generation sequencing is trying to do a genome scale profiling of your cells or specific subject or patient. So basically, we are looking at all possible gene expressions in human cells, for example, if we are studying human disease. So it provides us a genome scale profiling or characteristics of how things look like. And the data type is essentially a count data, right? So basically, we are trying to collect the cell samples and then trying to extract the DNA sequence or RNA sequences and then map those short reads to the reference genome and count how many short reads are mapped to a specific region and use that as concentration levels or expression levels of that specific segment. So essentially, that's the data nature. So it's a count data. It's not a Gaussian data. So we somehow needed to, again, probably scale model this count nature of the data. And then, right, so in the past, basically a few years, we have seen, starting from the beginning, it's a bulk RNA-seq. So you get a bunch of cells, and then you basically have the convolved gene expressions from this group of cells instead of looking at a specific cell characteristics. And then recently we have this single cell RNA sequencing. So basically it zoom in to the single level individual cell resolution. And more recently, we have this special transcriptomics, essentially not only trying to look at the cell gene expression, but also you want to kind of locate where cells are coming from different tissue organs, etc., so that you can basically to be location specific when you are trying to analyze your expression profiles. So this is what you can do with those RNA sequencing technique. So the first thing is that you can kind of do the clustering or subtyping of different cells to understand what's their development stage or what's their tumor risks for different groups of cells. And then you can do some differential expression across those different subtypes so that you can derive certain signatures or biomarkers of different development stages or different subtypes of diseases. And then you can also try to kind of have a dynamic model to understand how cells are evolving based on their gene expression profiles. And then at the end, if you're interested in understanding the metastasis of the tumor cells, then you also can characterize the cell-cell communications to see how tumor cells are invading the healthy cells so that you can derive potential intervention strategies, right? So this picture is coming from this single cell RNA sequencing paper. So essentially, what we are seeing is that from whatever sequencing technologies, this is the data set you are going to have. So basically, the rows are a number of genes in the cells, columns are a number of cells you collect the data from. So basically, we are going to analyze this data types. And then the first thing what you can do is to do the subtyping or clustering to see how those different cells look like each other. And then you color them. And then based on whatever the latent space layout, then you can do a pseudo-time, mapping to make sure like what's the development lineage of those different cells to understand what's the underlying cellular mechanism. So that's what a single cell RNA sequencing can help you to do. All right, so actually this is like basically the typical analysis pipeline. You definitely need to do data preprocessing, normalization to get the more, how to say, well quality controlled counter matrix. Then you start from analyzing this counter matrix to do whatever the consequent analysis tasks. So basically, you can do the gene level analysis as well as cell level analysis, as I kind of briefly talked about at the previous page. Now, so this is actually one data probabilistic model we use to model the single cell RNA-seq data. So I kind of emphasize that RNA-seq data is a counter data. So instead of using Gaussian model, basically what we are using is a negative binomial model. And the negative binomial model essentially has two model parameters. One is the probability, one is the shape parameters. So we have kind of some interesting design of how to model those shape probability parameters. So especially there are like two shaded circles here. Essentially ZV is basically modeling whatever characteristics of the specific gene or specific segments of the RNA sequences. Right, so V basically is the gene index, and J is essentially the cell index. So XJ essentially models how cells are different. Right, so for example, if you indeed put some intervention or treatment with a drug or without drug, so XJ could be 0 and 1, and it will affect your gene expression. Right, so based on this kind of a model setting, then we can do differential expression analysis. So we can do subtyping, or we can try to put a dynamic modeling if you want to model the cell development on XJ. Right, so I mean, I guess this is, again, traditional statistical way to infer the model. It's basically just a give sampling based on conjugacy of the probability distributions of those model parameters. So that's what we did for single cell. And recently we did it similarly for the special transcriptomic data. So the difference of a single cell from the, special transcriptomic data from single cell is that you can see that it maintains the locations in the tissue, right? So that you can actually identify which cells are actually problematic cells. So if you want to do the targeted precision medicine, then you can target it to those specific groups of cells. But anyway, so again, it's a count matrix. And in this specific case, then because expense of doing special transcriptomics data, so mostly it's not at the individual cell level. So it's still at the spot level. So each spot contains multiple cells. So because of that, one important data processing technique to analyze the ST data essentially is doing deconvolution to make sure, like at that spot, how many different types of cells you have and recover its gene expression profiles. Right, so that's essentially what we try to do. So this is a kind of our model to do that. Like what I said, actually you have both gene expression matrix, again, a counter matrix, as well as their special locations of each spot, right? So how do you kind of leverage the special location, making the assumption that nearby cells are going to be very similar, right? So essentially you are adding some knowledge here using this horseshoe prior. So basically saying the expression profiles or characteristics are going to be similar in the geometric neighbors, right? So what we did actually on top of that essentially is talking about what if you actually have multiple samples when you are looking at the same problems? So how you can actually further incorporate the similarity across different sample, different slides of ST data. So basically what we developed is a kind of, based on gene expression profile similarity, then we try to add this new horseshoe prior to constrain the to better borrow the signal strengths and get better results. So in fact, we did a validation for this bone marrow cancer, and we identified those potential tumor cells. And if you do the microscopic image to check whether indeed there are kind of cancer cells, indeed we can match fairly well on those identified cell groups. I'll jump to actually the title. So this is another way to incorporate the prior knowledge and explicitly model the data types. So for these data types, we are talking about the dose-dependent response. So essentially, if your cells get exposed to radiation, chemotherapy, because those are kind of ordinal vectors, right? Ordinal variables. So instead of, again, using Gaussian random variables, we explicitly model the ordinal nature. And then in this, basically in this kind of variational autoencoder, one thing is you want to guide your AI machine learning models to identify the gradual changes of your cell characteristics because of you're applying different dose levels. And another thing is here, right? So this Z, the typical variational autoencoder, if you are familiar with this model, is kind of random. You kind of set a prefixed dimensional latent vector and then do the encoding, decoding to reconstruct the gene expression. But in this specific example, I actually used this model. I'm sorry for that, but so this S is a mask. Essentially, it's based on the pathway. So you are going to basically building up this kind of binary matrix to associate the genes to each pathway. And that latent space specifically capture the pathway activity. The reason is, again, because of small data. You want to, if you want to kind of derive reproducible, robust signatures or biomarkers, pathway signatures probably is more stable or robust than individual gene level methods. So let me quickly show you the results. So indeed, we can identify the gradual changes in different pathway activities. We can identify which pathways respond to radiotherapy, chemotherapy more, so that the doctors can probably design better therapy strategies. All right, so with that, I'll just, I'm sorry for that.
Thank you very much. And again, we're out of time, so if we could hold our questions. And I neglected to mention that Xiaoning is also one of my colleagues in computer science. So we have Jonathan Siegel coming up next, who is clearly the future lies. Either you're going to join the computer science department or you're going to become a colleague of mine. I don't know which, but I look forward to figuring out which one that's going to be based on the probabilistic of the last 4 sessions. Probability. So without further ado, we'll have our last speaker of this session, and then we'll do our question and answer panel.
Right. Yeah, thank you very much. I want to thank the organizers. I'm very happy to be here, and thank you all for your attention. Oh, right here. Okay, got you. Yeah, so my name is Jonathan Siegel, and I'm in the math department. So I work on trying to solve math problems, and we always hope that these problems end up being useful. So today I'm going to talk about something we've been working on recently, which I think may be useful to people who want to apply AI to, or neural networks or machine learning to problems in science or medicine. Okay, so this is the outline of the talk. I'll give a brief introduction, talk about properties we would like these models to have for scientific problems, invariance and continuity, and then talk about some solutions to enforce that and some experiments. Okay. So introduction, recently neural networks, as we all know, have revolutionized many areas of machine learning. I just want to give a very brief introduction and say that for our purposes, or for my purposes in this talk, a neural network is really just a function of some input, which is just a list of numbers, right? Put a bunch of numbers in on one end, and you get out an output, right? And this function is parameterized by a bunch of weights and biases. A bunch of parameters. Okay, and this model has proved to be remarkably successful for a lot of applications, including recently people have applied them to scientific problems. So for example, this is sort of the type, there are many different scientific problems people have applied these to, but the type of problem that I have in mind in this talk is something where, for example, you want to input a molecule or some, molecular structure into the neural network and have it predict a property, like, for example, in this figure, the formation energy, input basically a molecule or some sort of chemical structure and have it output some problem. That's the type of application I'm kind of thinking about. So how would you go about doing this, really? I mean, a fundamental question is, well, how do we input a chemical structure into a neural network, right? The input basically has to be just a list of numbers. So kind of a fundamental way to do it. There are perhaps other approaches, but sort of maybe a natural way to do it would be to just input the types and positions of all the atoms, right? So you input the network, well, you've got, you know, carbon atom here, oxygen atom here, et cetera. Right? Now, if you do this, then the network should have, or your model should have some properties. Namely, it should be invariant to certain transformations of the input, right? If you reorder the atoms, it's the same molecule, so the network should have the same output, right? Or if you rotate the molecule, give it if you rotate the molecule, again it's the same molecule, so the network should have the same output. So you should have the network, whatever model you're using, it doesn't even really have to be a neural network. Whatever model you're using should be invariant to these groups here, right? And so mathematically, you would say that the function that the neural network represents should not change if you apply a rotation or a permutation to the input. Okay. And another property that the neural network should have is it should be continuous. So if the neural network function should have is it should be continuous. So if you change the locations of these atoms slightly, the property should not change dramatically. And so these are kind of two properties that the science essentially tells you that reality has these two properties, right? So your model should also have these properties. If it doesn't, you could get an output that's not really scientifically accurate, or you really need more data because the network has to learn these from data instead of having to build. So the problem with this is that the standard networks people use, these feed-forward networks, do satisfy continuity, right? The output will be a continuous function of the input, but they're not going to be invariant to these groups. They're not going to be invariant to permutations or rotation of the input. And so there are a variety of ways to attempt to fix this. So one thing you could do is to design special neural networks that do satisfy the right invariance. This can be done pretty well for the permutation group, but it's a lot more difficult and doesn't really work so well for rotations. But that's not really the approach. And it also has the disadvantage that you have to choose a special architecture. You can't use some sort of off-the-shelf architecture, which is very common in the practice of deep learning. And so we want to consider a different approach, which is to canonicalize the input, essentially say, well, I'm not going to, I input my molecule, I always want to rotate it into a pre-specified orientation and sort the atoms in a pre-specified way. This I'll call canonicalization. So transform the input into some canonical form before I put it in. The problem, mathematically, this just means that I've got some function that maps any particular input to a canonical. Okay, so the problem with this is that it can break continuity. And here in this slide, you can see an example of this on the far left. You don't break continuity. This is a situation where canonicalization can be done well. You basically, if you just have a list of numbers and you want the network to be invariant under permutation of these numbers, you can sort them, right? So that gives a very natural way of ordering the input, and it will preserve continuity. So if you slightly perturb and then sort, you still get something close to the sorting of the original input. However, if your input is now a point cloud and you want it to be invariant under permutation, then it does break continuity. So that in 2D, right, there's no kind of natural way of sorting a point cloud. So if you just say, well, I'll sort it lexicographically, that works, but unfortunately now you're breaking continuity because a small perturbation of your input point cloud can dramatically change the order in which you now sort it, right? And similarly for rotations, there's also this issue where trying to canonicalize breaks continuity. And it turns out that this is not just an artifact of the particular way we've chosen to sort here. It turns out we can show that there's actually no possible way to canonicalize in a continuous manner for a variety of situations of interest, in particular where you have permutations or rotations acting on point clouds. Okay. So our solution to this is to introduce what are called weighted, what we call weighted frames. So instead of basically feeding a single input, taking a given molecule rotating in a specified way and feeding a single input into your neural network, you rotate it in a bunch of different ways, feed those all into your network, and then average the output in a certain way. Okay, which is illustrated in this figure. Now, of course, this is going to be a bit more expensive because you've got to feed multiple things into your neural network. And so, the key question that we then looked at is, well, how many elements do we need to average over in order to still be able to guarantee continuity? You could always average over the entire group. So you could always say, I average over all possible permutations of my point cloud, but that's going to be impossibly expensive very, very quickly. And so basically, this is the problem that we've studied. And for the examples that I have talked about here, so permutations and rotations acting on point clouds, we can construct weighted frames of a reasonably small size. We're still kind of trying to determine what the optimal, best possible size is, but we can do it for these two examples. So let me conclude by showing some experiments of what the effect of using this is. And the experiment I want to consider here is, so there's this MNIST data set, which I imagine most of you are familiar with. This is 30 years old, and essentially what it consists of is digits, pictures of digits, and then corresponding labels. And you want to classify each of these written digits to the correct number. Now, doing this with a neural network is trivial, essentially. But what we're going to do is we're going to add a little twist here. We're going to basically, instead of giving the neural network the actual image, so the pixel values at every point, I'm going to turn these digits into a point cloud. So basically draw, sample of sort of 100 different points that are inside of the written image, right? So look at where is the pixel value 1? I take like 100 points in there, and now I feed the neural network this point cloud in a random order, and want it to ask it to classify what digit that is. So I turn these images into a point cloud, sort of to emulate, maybe the situation you have if you're inputting a molecule, the positions of atoms into your neural network, right? Makes the problem a bit harder to classify. And so now if we look at the results here, so the training details are not really particularly important, but we basically use a standard architecture with 5 hidden layers and try to classify this. And now if you do nothing, if you just feed this list of 100 points into your neural network, your test accuracy ends up being not too good, 26%, right? Because you're not building the invariance into the network, so you can't really learn how to classify these digits properly. So that next thing we tried is to sort lexicographically. So now you are making things invariant, but you're breaking continuity, and you do a lot better, 85% test accuracy, but still not as well as if you use developed, which ensures that you are both invariant and continuous. So by preserving both invariance and continuity, you can essentially get more out of your data and end up getting higher test accuracy. And if you attempt to average over the whole group, it's essentially computationally so expensive that it behaves as if you not. So, yeah. To conclude, we've developed what we're working on still currently is developing methods for making neural networks invariant to different group actions, and we expect that this will be useful in applications of deep learning to scientific problems. So if any of you have some relevant problems or data sets, I'd be happy to talk to you and see if our techniques can help you. Thank you.
Thank you very much, Jonathan. Again, we're going to hold questions, but I do hope that the many people in here who have taken my sketch recognition class saw that he's probably going to be a collaborator, at least presenting in sketch recognition class coming in the future. So with your methods of recognizing digits, can all of the presenters please come up here for at least one question? Yes, everyone can sit at the table. Okay, so my big burning question, and this is actually related a lot to my work with Paula, it was another collaborator of mine. Hindsight is always 2020. Okay, each of you are working on very different applications of AI on health, or numbers or but very different applications of AI. My question to you is, I'm very passionate about ethics. So thinking about your research, what are the potential, you talked about how amazing your research is. What are the potential threats that your research might bring to the table, or what are the ethical implications that your research has? And do you want to go first?
I'm working with some people on clinical genomics, and what they talk about is privacy and security, who owns your data and what's going to happen to it. I think that's why AI has both a good and a bad name, is that fear of use. So we have to have policies in place so that use is protecting privacy and security.
Fantastic.
I'd like to piggyback on the privacy issues, because what we are doing is to develop an open source autonomous driving system. And we also have gathered data from our users as well, and how to make sure that we can well protect the security, the privacy. All of those data is very important. And oftentimes people who have no idea about AI, and they just feel very anxious about a lot of information you gather from them. I said, what about, are they going to steal this from me? Are they going to steal that from me? What about some hackers get into a car and everybody will be killed? So those type of questions are, are very, very important. So I think when the scale of operation gets bigger, those questions will become even more burning. So I would welcome any colleagues in this room who have talents, who have expertise in data security and privacy, to collaborate with us, and we have the playground for you to implement the cutting edge methods for those issues.
Sure. So I can talk about, because I kind of talk about how to integrate the knowledge extracted from literature. So in general, when we are talking about generative AI, so essentially there are lots of hallucination, misinformation you could get from those ChatGPT, etc. So how to take care of those misinformation, hallucination. And now if we talk about drug design, materials discovery, so we definitely need some regulations to make sure we are make the world better instead of worse. So how we make the rules, regulations, and laws to make sure that actually happens in the right direction could be something we can think more. And also education, really do we want to completely rely on AI to do the education? How we indeed involve a human being, make human really do the decision making instead of AI doing the decision making. That's potential another kind of AI related research directions, especially for healthcare, right? So we have been talking about the personalized medicine, human-centered healthcare. So again, I heard Marcia say about AI is just a tool. So human is still in the center in the sense how we can guarantee that that's indeed the case in future. Probably needs some study. Yes.
Yeah, I mean, so I think that the tools that we develop as researchers in machine learning or adjacent fields, can always be used in productive and also destructive ways. And I think it's important that they're as transparent as possible, so that as many people understand them as possible, as many people have access to them as possible, so we don't have end up having a small group of people making decisions about these tools for everyone else, essentially. So I think keeping everything open, doing research as openly as possible is important. But I don't personally work with any specific data or anything, so I haven't really had to worry about more subtle issues like that yet.
Yeah, I don't have too much to add, but I thought, in computer science, cybersecurity has become very big, isn't it? I think eventually this may become something similar to that, hopefully. Like this AI security, maybe in the end we develop into something like its own field, hopefully. And we can have like built-in mechanism to protect or something like that. So that's what I think. I hope that will happen.
I want to add one. Okay. So it's about, this is something that most striking to me. So when we introduce the idea of implementing autonomous vehicle in a small town, serving people in need, most people love it. But there are people who are very, who are not very interested in it, and they are honest with us. We don't like autonomous vehicles because they're going to take away our jobs. We want people to drive cars and serve people, and especially the people who work in the community. They are truck drivers. They are very sensitive to using autonomous vehicles in community take away people's jobs because the industry has messed up and they are basically taking away jobs and like that. So I think the philosophy that I emphasize many times to our team members are that, hey, we use autonomous vehicles at places where people don't want to drive. Because imagine we only serve places where there is no Uber or Lyft drivers who are willing to serve these small towns. So I realized that when I explain this to them, that, it's just like we deploy autonomous vehicles in a very toxic, very dangerous setting where human drivers, it's not appropriate for human drivers to do it. I think that way will help the community to accept the use of AI to solve problems. People don't like jobs to be taken away. People like to see that you use technology to create solutions and make everybody's life better.
Great. I want to just ask one last question, if you don't mind. Oh, well, can I ask my question first? Is there somebody else? I wanted to add it's a follow-up question, which is why I wanted to ask it. The first question was sort of my computer science hat. I want to put on my engineering education hat. And when I think about what am I afraid of in terms of AI, it is the fact that it is so ubiquitous right now, and it makes any nefarious actor incredibly powerful. And there are already people using AI to do drone attacks and in military warfare and these sort of things. So when we think about that, and we also think about the fact that whether you like it or not, our school is a huge feeder school for CIA, NSA, a lot of things to protect national security. How do we educate our students to make sure that they understand the ethical implications of those tools, the AI tools that they're working with and developing? Anyone want to go after that?
I guess, the only way I can think of it is get hands dirty. You have to try it. Without trying it, I guess you don't really know the power of it, what an AI can do and what harm AI can do in a sense. So my feeling is that no matter what kind of disciplines, like at least on the frontier of the research, people are already deploying AI methods on many, many disciplines. So education-wise, no matter which departments or which subjects you are doing, maybe we should have some AI practice, kind of either transdisciplinary or interdisciplinary courses in each department. So that's what I would.
I think AI is like any new technology. The next generation has to understand the pros and the cons. They need to understand how to use it, what are the best circumstances, and use it wisely. So I think AI is just the latest technology but we need to educate our students in the next generation of workers more broadly.
I tell my students that AI of today is just like electricity 100 years ago. It's going to become a general technology that all industries need electricity. In the future, all industries, all disciplines need AI. You like it, you don't like it, It's going to happen. It's there. It's already very powerful. Everybody can see it. So I tell my students, urban planners, to be on the winner's side and not on the loser's side. So this semester, starting this semester, I tell them, hey, everybody create a 40 minutes video, a tutorial to teach fellow urban planners about how to use AI to solve urban planning problems. Yesterday was the deadline, and many students are very stressed out. But I love seeing that.
My perspective is that I think most students are now stay at the level of the ChatGPT. That's the most familiar to them. I guess most importantly, we should teach them to use it constructively. I think you can even generate code these days, isn't it? It could be dangerous. So I guess we should start from there. That's what I want to say.
Yeah. I mean, I think students generally are, as far as I've seen, are very excited about using these new AI tools for different things. And, I think, it's important for us to teach them that not everything you do with ChatGPT is a good idea, right? And but we also have to figure this out too. So, yeah.
Thank you all. Do we have time for one audience question? Is there, we're out of time? Okay, well, I apologize for no audience questions. Hopefully my two questions were exciting enough and provided a little bit of thoughts of these 5 brilliant researchers here. So let's thank our panelists.
We want to thank the organizers. This is an amazing workshop that you put on. And my sense is this is just the beginning of collaboration, not the end.
Yeah. Thank you. Thank you.